Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, questions take their time, and the universe is allowed to speak in a quieter voice. Tonight, we're looking up at something that feels a little strange once you notice it. The night sky above us is full of stars. Some are young, some are old, some are enormous, unstable, and living on borrowed time. Our galaxy, the Milky Way, contains hundreds of billions of stars, vast clouds of gas, stellar nurseries, collapsed remnants, wandering worlds, and more than a few cosmic troublemakers. It is busy, it is active, it is not a sleepy place. And yet, for all that activity, there is a silence where we might expect thunder. Because somewhere in this galaxy, stars should be exploding, not gently, not politely, but with the force of a star tearing itself apart in one final event known as a supernova, a blast so bright it can outshine entire galaxies for a time, a flash visible across enormous distances. A stellar farewell powerful enough to forge heavy elements, shock nearby gas clouds, and leave behind strange remains like neutron stars or black holes. So here is the question that will carry us through tonight's slow and curious journey. Why haven't we seen one here? Why has our own galaxy, packed with stars and stretching across roughly 100,000 light-years, not treated modern humanity to a clear, unmistakable supernova blazing overhead? Where is the next great explosion? Has the Milky Way gone quiet? Or are we simply missing what is already happening? Before we settle into that mystery, I'd love to know where you're listening from tonight and what the sky is like there right now. Is it cloudy, clear, bright with city lights, cold and still? Maybe there are stars above you already, doing what stars always do, shining patiently while we try to understand them. And if you find this little voyage soothing, interesting, or simply a pleasant way to unwind after a long day, I'd be ever so grateful if you liked the video and subscribed. It helps this calm corner of science drift toward other curious minds who may need a softer ending to their evening. Now then, get comfortable, let your shoulders drop, let the day loosen its grip a little. We're going to spend some time with a paradox. We live inside a galaxy that should be dramatic, but lately it has seemed remarkably well behaved. That may sound odd because space often gets described as empty and quiet. In truth, it is full of events. Stars are born in dense molecular clouds where gravity gathers cold gas into tighter and tighter knots. Young stars flare and spit radiation. Giant stars lose mass in fierce stellar winds. Smaller stars settle into long, stable lives. Binary systems tug on one another. Black holes feed. Planets collide, comets wander, dust drifts, magnetic fields twist. The universe is not inactive. It is merely large enough that much of its activity happens elsewhere. Still, some events are so energetic they announce themselves loudly, even across cosmic distances. Supernovae belong in that category. They are among the brightest stellar events known. If one happened close enough, it could become visible in daylight. If one occurred on the far side of the galaxy, it might still be detectable through instruments, radio telescopes, neutrino detectors, infrared surveys, X-ray observatories, and a long list of devices humans have built because we simply cannot resist checking what the sky is doing. And yet, when people think of famous recent supernova, they often think of explosions in other galaxies. The Large Magellanic Cloud gave us SN 1987A, a spectacular nearby event but not inside the Milky Way proper. Telescopes regularly spot supernovae in distant spiral galaxies, elliptical galaxies, irregular galaxies, galaxies with names that sound like catalogue numbers because astronomers are many things but rarely poets when filing paperwork. We see other galaxies lighting up. We see remnants of old explosions in our own galaxy. We see stars that appear capable of exploding someday. But in the modern era, no unmistakable naked-eye supernova has risen over Earth from within our galaxy in the way ancient observers once recorded. That gap feels surprising once you sit with it. Imagine living in a forest full of trees known to drop the occasional thunderous branch, and for centuries hearing stories of crashes in the past, seeing broken limbs on the ground, noticing leaning trunks everywhere, yet never witnessing the event yourself. You might begin to wonder whether the forest had changed, whether the danger was exaggerated, or whether you simply kept looking the wrong direction at the wrong time. That is roughly where we are with galactic supernovae. The history of astronomy tells us that humans have seen some before. Bright new stars were recorded by observers in places such as China, Middle East, and Europe. Some of those mysterious lights were almost certainly supernovae. They appeared when no bright star had been seen before, lingered for weeks or months, then faded. One of the most famous was the event of 1054, which produced the remnant we now call the Crab Nebula. Another came in 1572, observed by Tycho Brahe, another in 1604, associated with Johannes Kepler. So the sky once offered visible stellar explosions, often enough to enter written history. Then, for modern sky watchers, nothing comparable overhead. That does not mean nothing happened, it means nothing obvious happened. Those are very different statements. One of the easiest mistakes in astronomy is assuming absence of spectacle means absence of activity. If a supernova erupts behind thick curtains of interstellar dust, visible light may never reach us clearly. If it occurs on the far side of the galactic disk, crowded fields of stars and gas can hide it. If it happens in a region most people no longer watch carefully with dark adapted eyes, because city lights have replaced darkness, it may not receive the dramatic cultural attention it once would have. And of course, timing matters. Human lives are short. Civilizations feel long to us, but in stellar terms they are barely a glance. If the average rate of supernovae in the Milky Way is a few per century, that does not mean one politely arrives every 50 years on schedule like a commuter train. Nature does not keep appointments for our convenience. There may be clusters and gaps. There may be decades of nothing followed by multiple events. Statistics often sound smoother than reality. If I tell you that a bus arrives every 10 minutes on average, you know perfectly well that some evenings you may wait 25 while reconsidering all life choices. Galaxies are much the same, only larger and less apologetic. Another wrinkle is that not all supernovae are equally visible. Some are brighter than others, some evolve faster, some occur in environments that swallow much of their light, some may direct more energy into wavelengths human eyes cannot see. What counts as "we would definitely have noticed" depends heavily on where, when, and how it happened. Then there is the modern expectation that science knows everything immediately. We live with alerts, feeds, live maps, notifications, automated telescopes, and the comforting illusion that if something major happens, our phone will vibrate within seconds. Yet the sky is bigger than our systems. There are blind spots. Daylight hides stars for half the planet at any given moment. Weather blocks observatories. Instruments undergo maintenance. Data waits to be processed. Signals can be subtle before they become obvious. Sometimes the universe still gets to surprise us. That possibility is part of the charm. Consider also how dramatic a true nearby supernova would feel now. Ancient people often treated unusual celestial lights as omens, wonders, warnings, or divine messages. Modern people would likely do something equally organised and rational, such as posting blurry videos, arguing online, buying emergency supplies for reasons no one can explain, and asking whether it affects Wi-Fi. Meanwhile, astronomers would be having the most exciting week of their professional lives. Every telescope possible would turn toward it. Data archives would overflow. Spectra would be captured hourly. News anchors would learn to pronounce stellar names under pressure. Someone somewhere would definitely say, "This changes everything," even if it only changed telescope scheduling. But before we get to what the next supernova might look like, we first need to understand why the current quiet may be less mysterious than it seems. because hidden beneath the silence are clues. The Milky Way is not transparent. It contains lanes of dust thick enough to block visible light. We know stars continue to form in regions we cannot see directly with ordinary eyes. We know massive stars live short lives, meaning some are surely ending even now somewhere behind obscuring material. We know remnants scattered across the galaxy mark explosions from the past. We know neutrinos and other messengers can reveal events light alone might conceal. In short, the galaxy may not be quiet at all. It may simply be complicated. That distinction matters because astronomy has often advanced when humans realized the universe was not lacking phenomena, only hiding them behind the limits of our senses. We thought planets were wandering lights until better models arrived. We thought nebulae were clouds inside our galaxy, until some proved to be galaxies themselves. We thought the cosmos was static until expansion became clear. Again and again the sky was doing something interesting before we noticed. So perhaps the current supernova mystery belongs to that same tradition. Maybe the question is not, why haven't there been explosions? Maybe it is, why are we expecting explosions to announce themselves in the narrow way we prefer? Visible light flatters human intuition. It lets us point and gasp. But the universe communicates in radio waves, infrared glow, X-rays, gamma rays, neutrinos, gravitational ripples, and subtler signatures than a bright new star over the rooftops. We're gradually learning to listen in more than one language. And as we do, the apparent silence begins to soften. Somewhere out there, an aging red supergiant may be nearing collapse. Somewhere else, a white dwarf in a binary system may be stealing matter from a companion, edging toward catastrophe. Elsewhere, remnants of past blasts continue expanding quietly through space, long after the fireworks ended. The galaxy keeps busy schedules no human calendar tracks. For now, though, the central mystery remains a lovely one to hold in the mind as the evening settles around us. A galaxy filled with stars, a history that says explosions happen, a present that feels oddly calm, and a question hanging over it all. If stars do sometimes die spectacularly in our cosmic neighbourhood, what exactly are these events we're waiting for in the first place, and what does it truly mean when a star explodes at all? Settle in again for a moment, because before we can ask why something has not appeared in our skies lately, we should understand what that something actually is. The word supernova sounds dramatic, and to be fair, it has earned that reputation. It suggests grandeur, danger, bright flashes, and astronomers suddenly forgetting to eat lunch because data is arriving too quickly. But despite the name, a supernova is not simply a star getting a bit brighter than usual. It is not a large spark. It is not a stellar sneeze. It is one of the most violent transformations a star can undergo. At its simplest, a supernova is a powerful stellar explosion that occurs when certain kinds of stars reach the end of a long physical struggle. For a brief time, the star can release more light than billions of ordinary suns combined. Matter is hurled outward at tremendous speeds. Shock waves race into surrounding space. New elements are forged. Sometimes a compact remnant is left behind, such as a neutron star or a black hole. Sometimes the original star is destroyed almost completely. So when astronomers say a star exploded, they do not mean it casually. They mean that nature took an object with a mass far beyond ordinary comprehension, destabilized it, and turned it into an event visible across galaxies. That may sound sudden, but the road to a supernova is usually long. Stars spend most of their lives in balance. Gravity pulls inward, always trying to compress the star. Pressure from nuclear fusion pushes outward, resisting collapse. Deep in the core, hydrogen atoms are fused into helium, releasing energy. That energy moves outward and eventually escapes as light and heat. As long as fusion continues strongly enough, the star remains stable. You can think of a star as a long negotiation between gravity and energy. Gravity never gives up. Fusion keeps answering. For millions or billions of years, depending on the star's mass, this arrangement can continue. Our own sun is in such a stable phase right now. It is not on the verge of exploding. It is busy being dependable, which we appreciate, but not all stars are equally calm. Massive stars burn fuel at astonishing rates. Oddly enough, having more fuel often means a shorter life. A very massive star has stronger gravity, creating hotter, denser conditions in the core. Fusion runs faster. Enormous stars can consume their fuel in only millions of years, while smaller stars may last for tens or hundreds of billions. That means some stars live fast and end loudly. As hydrogen becomes scarce in the core, the balance changes. Gravity compresses the center further, temperatures rise and new forms of fusion begin. Helium may fuse into carbon and oxygen. Later stages can create heavier elements in successive shells, rather like layers in an onion. The star swells, shifts, pulses, and becomes more unstable. Eventually, for the most massive stars, the core reaches iron. Iron is trouble. Fusion up to iron can release energy under stellar conditions, but fusing iron into heavier elements does not provide the same outward support. It consumes energy rather than supplying it. Once a massive core becomes dominated by iron, the star is approaching a dead end. At that point, gravity has been waiting patiently for millions of years, and gravity collects. Without enough outward pressure, the core collapses in a fraction of a second. Temperatures soar, densities become extreme, electrons and protons may be crushed together into neutrons. The inner core stiffens abruptly, and in falling matter crashes into it. A shock wave forms. Neutrinos flood outward in staggering numbers. If conditions are right, the outer layers are blasted into space. That is one classic path to a supernova, often called a core collapse supernova. A star spends ages building itself, then loses the argument with gravity almost instantly. The scale is difficult to picture. Imagine something larger than our sun releasing in days the energy our sun emits over billions of years. Even comparisons struggle here. Supernovae sit in a category where ordinary intuition becomes less useful, and yet not every supernova begins with a giant star. Some begin with the remains of smaller ones. When stars like the Sun eventually exhaust their fuel, they do not explode as supernovae. They shed outer layers and leave behind a dense core known as a white dwarf. A white dwarf is roughly Earth-size but contains mass comparable to the Sun. Matter there is packed so tightly that quantum physics helps support it. Left alone, a white dwarf can cool slowly for ages, but if it lives in a binary system with a nearby companion star, things can become less peaceful. Gas may spill from the companion onto the white dwarf. Over time, the white dwarf gains mass. If it approaches a critical limit, internal conditions can trigger runaway thermonuclear fusion. Carbon and oxygen ignite rapidly throughout much of the star. Instead of collapsing first, the star undergoes an enormous thermonuclear disruption. That is another major kind of supernova, often called Type 1a. In many such cases, the white dwarf is effectively torn apart. So already we find that the term supernova includes more than one story. One path involves a massive star collapsing under its own gravity. Another involves a stellar remnant becoming unstable and igniting catastrophically. Different beginnings, similar brilliance. This matters because when we ask why we have not seen a recent supernova in the Milky Way, we are asking about several populations of stars, several timescales, several mechanisms, and several chances for nature to surprise us. The word nova can also confuse people. Historically, astronomers used nova for new star because a bright point appeared where none had been noticed before. Today, a nova usually means something less extreme than a supernova. In a nova event, material falling onto a white dwarf ignites on the surface, causing a dramatic brightening, but the star survives and may repeat the process. A supernova is the much more serious version. A nova is the smoke alarm. A supernova is the house leaving the neighbourhood. Brightness is another tricky point. We often say a supernova outshines a galaxy, but that statement needs context. A galaxy contains vast numbers of stars, yet most are modest. During peak output, a supernova can rival the total visible light of its host galaxy for a short time. That is why astronomers detect them in distant galaxies at all. Something extraordinary has happened if one star suddenly competes with hundreds of billions. Then there is what remains afterward. Core collapse supernovae often leave behind neutron stars. These are objects of astonishing density. A teaspoon of neutron star matter, if somehow sampled without ending civilization, would weigh more than mountains. Some neutron stars spin rapidly and emit beams of radiation as pulsars. If the collapsing core is massive enough, even neutron pressure may fail, and a black hole can form. Meanwhile, the expanding debris creates a supernova remnant, glowing for thousands of years as shockwaves energize surrounding gas. Famous remnants such as the Crab Nebula are long-lived afterimages of stellar death. So a supernova is not just a flash. It is a beginning disguised as an ending. The heavy elements around us owe much to such events. Iron in blood, calcium in bones, oxygen in old stars' descendants, gold and other heavy materials produced in violent astrophysical processes. Many ingredients of planets and life were forged in ancient stellar furnaces and scattered by explosions. When you hold a metal spoon, you're touching matter with a dramatic family history. That may sound grand, but it is simply chemistry with excellent publicity. Another common misconception is that stars choose to explode when they run out of fuel. In reality, fuel exhaustion is not like a car engine stopping. For stars, running low on one fuel source often changes pressure conditions, causing contraction and heating that can ignite another stage. The path to death is dynamic, not passive. Supernovae happen because physical balances shift beyond recovery. There is no mood involved. Stars are not temperamental. They're obedient to equations. Still, those equations can create astonishing endings. Timing adds another subtlety. If a massive star is 10 million years old, that may sound ancient to us. Cosmically, it is young. If a smaller star lives 10 billion years, that may sound impossible to everyday intuition. Yet many red dwarf stars will outlive the current age of the universe. Stellar lifetimes vary wildly. So when we look at the sky, stars are not all in the same phase. Some are infants hidden in gas clouds, some are steady adults. Some are swollen elders, some are remnants, some may already have exploded, their light still travelling. That last point is always worth pausing over. We do not see stars as they are now. We see them as their light was when it left. A star 1,000 light years away is shown to us 1,000 years in the past. If it exploded yesterday, we may not know for centuries. If a nearby star exploded centuries ago, we might already be seeing it. Astronomy is observation mixed with delay. The sky is a museum with live updates. Now, if a supernova occurred near Earth, would it be dangerous? That depends strongly on distance and type. Many would be mainly spectacular. A sufficiently close one could affect atmospheric chemistry or increase radiation exposure. But truly hazardous distances are generally small compared with the scale separating us from most candidate stars. The galaxy is large, and we are not standing in the middle of every problem. Usually, a supernova would be better described as awe-inspiring than threatening. Though headlines would likely prefer threatening, modern instruments also allow us to detect supernovae before visible light peaks. Neutrinos, those elusive particles produced in vast numbers during core collapse, can escape stellar interiors rapidly. If detectors catch a neutrino burst from a galactic event, astronomers may receive warning hours before the explosion brightens optically. Imagine getting advance notice that a star is about to become the most interesting object in the sky. That is the kind of message scientists dream about. There is also beauty in the fact that destruction and creation are linked here. A supernova tears apart a star yet enriches space with new material. shock waves can compress nearby gas clouds, helping trigger future star formation. What ends one system may seed another. Not mystical, just practical. The universe recycles with enthusiasm. So when we ask, what is a supernova really? The answer is broader than one sentence. It is the collapse of balance. It is gravity or thermonuclear runaway winning decisively. It is the forging and scattering of elements. It is the birth of remnants like neutron stars and black holes. It is a beacon visible across immense distances. It is one of the ways galaxies renew themselves. And importantly for our larger mystery, it is not rare on cosmic timescales. Supernovae should happen in galaxies like ours often enough that the current quiet catches attention. Not constant, not nightly, but regular enough to make us wonder why modern observers in the Milky Way have not enjoyed a clear nearby example. Let's slow the pace for a moment and begin at the start, because stars do not arrive in the universe already blazing. They are not switched on like lamps. They are built gradually, shaped by gravity, patience, and an unreasonable amount of gas. When we look up at the night sky, it is easy to imagine stars as permanent things, fixed lights, ancient fixtures, reliable points in the darkness, yet every star has a life story. It begins, changes, ages, and ends. Some drift quietly into retirement, others conclude with enough violence to rewrite their local neighbourhood. And if we want to understand why supernovae happen, and why we may be waiting for the next one in the Milky Way, we need to understand how stars live first. Because catastrophe, in astronomy, is usually the final line of a very long biography. A star begins inside a molecular cloud, a vast cold region of gas and dust floating through space. These clouds are mostly hydrogen, with helium and traces of heavier elements mixed in. They can span dozens or even hundreds of light years. From a distance they may look peaceful. Inside they are messy places. Turbulence stirs material. Shock waves from nearby stellar winds or old supernovae pass through. Gravity constantly searches for any chance to gather matter into denser pockets. Eventually one region becomes heavy enough that gravity gains an advantage. The gas begins to collapse inward. As it contracts, the material heats up. The forming object at the centre becomes what astronomers call a protostar. It is not yet a full star. It has not begun sustained nuclear fusion in the core. It is more like a star under construction, wrapped in leftover dust, growing hotter and denser as gravity squeezes it tighter. Picture a campfire that has not yet caught flame, only warm wood and rising smoke. Then conditions cross a threshold. If the central temperature becomes high enough, hydrogen nuclei begin fusing into helium. This releases energy. That outward pressure pushes back against gravity. A new balance forms. A star is born. For most of its life, a star lives in what astronomers call the main sequence. This is the long stable period where hydrogen fusion powers the core. Our Sun is in this stage right now and has been for billions of years. Main sequence stars are the dependable adults of the cosmos. They shine steadily. They maintain balance. They turn mass into energy with quiet consistency. If stars held office jobs, this would be the spreadsheet era. But not all stars live the same kind of life. Mass changes everything. Small stars, known as red dwarfs, burn fuel slowly and carefully. They are the economical candles of the galaxy. Some may shine for trillions of years, longer than the universe has currently existed. None have yet reached old age because the cosmos itself is not old enough. Larger stars burn faster. Much larger stars burn recklessly. This surprises many people. Intuition says a bigger fuel tank should last longer. But in stars, stronger gravity creates hotter cores, and hotter cores accelerate fusion dramatically. A star 10 times more massive than the Sun may live only tens of millions of years. That is brief by stellar standards. These stars are bright, hot, powerful, and impatient. They live like someone spending next month's paycheck today. During the stable phase, inward gravity and outward pressure remain in balance. But hydrogen in the core is finite. Slowly, steadily, the supply changes. Helium ash accumulates. Core conditions evolve. Eventually, enough hydrogen is gone that the balance starts to wobble. Gravity notices immediately. The core contracts. As it contracts, it heats further. That heating ignites hydrogen in a shell around the core, and in many stars the outer layers expand enormously. The star swells into a red giant, or, for massive stars, a red supergiant. If our Sun became visible from afar during its future red giant phase, it would appear larger and more luminous, though cooler at the surface. It will eventually expand enough to dramatically alter the inner solar system. Fortunately, this is a problem scheduled billions of years ahead, which places it below tomorrow's errands. Massive stars enter even stranger later lives. Once hydrogen is exhausted in the core, helium fusion may begin, producing carbon and oxygen. When helium runs low, further contraction raises temperatures again. If the star is massive enough, carbon can fuse, then neon, then oxygen, then silicon. Each stage becomes shorter. Hydrogen burning may last millions of years, helium burning less. Later stages can last years, months, or even days. This is one of the remarkable details of stellar evolution. A star may spend nearly all its life in relative calm, then rush through a sequence of increasingly unstable final acts. Like someone calmly organising a house for decades, then trying to move everything in the last afternoon. Inside a massive aging star, shells of fusion can form around the core. Hydrogen burns in an outer shell, helium beneath it, then carbon, then oxygen. Layer upon layer, each governed by temperature and pressure, it resembles an onion structure, though one strongly discouraged from slicing. At the centre, the final destination approaches. Iron. Iron is where the easy bargains end. Fusion of lighter elements releases energy that supports the star. Iron does not cooperate in the same way. Fusing iron into heavier nuclei requires energy, rather than giving it back under these conditions. Once an iron core grows large enough, the star has lost its most effective means of resisting gravity. This is not a slow disappointment, it is a structural crisis. The core, no longer adequately supported, collapses inward at extraordinary speed. In fractions of a second, densities soar. Electrons are forced into protons, creating neutrons and releasing neutrinos. The inner region compresses until matter becomes astonishingly dense. Then the collapse rebounds. Material slams inward, hits the stiffening core, and a shockwave forms. That shock may stall and be revived by floods of neutrinos. If successful, the outer layers are blasted outward in a supernova. A star that may have spent millions of years shining steadily can destroy itself in seconds. That contrast is worth sitting with. Long preparation, instant decision. But not every star reaches this fate. Our Sun will not undergo core collapse supernova. It lacks the mass. After its red giant stage, it will shed outer layers into a glowing planetary nebula and leave behind a white dwarf. Despite the dramatic name, a planetary nebula has little to do with planets. Astronomers of earlier centuries simply named things with confidence and limited information. A white dwarf is the exposed hot core left behind. Roughly Earth-sized, incredibly dense, slowly cooling over immense timescales. So smaller stars fade. Massive stars explode. That is the simplified rule, though nature enjoys exceptions. There is another route to catastrophe involving white dwarfs in binary systems. If a white dwarf pulls matter from a companion star, it can gain mass. Under the right conditions, approaching a critical threshold can trigger runaway thermonuclear fusion. The white dwarf may be torn apart in a Type 1a supernova, so even stars too modest for a giant explosive ending can become dangerous later with the wrong company. A useful reminder for astronomy and life alike. Binary systems deserve special mention because many stars are not solitary like the Sun. They orbit companions. Some are in triples or more complex arrangements. Interactions between stars can strip outer layers, transfer mass, distort rotation, alter lifetimes, and create endings very different from isolated stars. A star's fate is not determined only by mass. It can also depend on relationships. Again, astronomy becomes suspiciously relatable. Rotation matters too. Rapid spin can mix stellar interiors, changing fuel usage. Metallicity matters, meaning the abundance of elements heavier than helium. Those elements influence winds and mass loss. Magnetic fields matter. Environment matters. Which is to say, stars obey physics, but the details are rich. No two biographies are identical. Now consider the timescales involved in our galaxy. The Milky Way has been forming stars for billions of years. Massive stars are born, live briefly and die explosively. Smaller stars continue shining. New clouds collapse. Old remnants drift. It is a continuous cycle. Gas becomes stars. Stars create heavier elements. Some stars return matter violently to space. That enriched matter helps form later generations of stars and planets. Without earlier stellar deaths, rocky worlds like Earth would lack many of their ingredients. The calcium in bones, iron in blood, oxygen you breathe, silicon in electronics, all depend on prior generations of stars manufacturing and dispersing elements. You are, in a very literal sense, made partly from previous stellar bookkeeping. This is one reason supernovae matter so much. They are not merely endings, they are distribution systems. They spread material into interstellar space, drive shockwaves through clouds, and help shape future star formation. The galaxy renews itself through both calm and violence. So when we ask why we have not seen a recent supernova, we are really asking where in this vast life cycle we happen to be standing. Some massive stars may already have died on the far side of the galaxy, hidden by dust. Some are nearing collapse now. Others were born too recently to be ready. Some white dwarfs in binaries may be quietly gaining mass. Meanwhile, countless smaller stars continue their patient, uneventful shining. The sky looks stable because many processes are slow, distant or concealed. But beneath that appearance, stellar clocks are running everywhere. One especially famous example is Betelgeuse. It is a red supergiant and a likely future supernova candidate on astronomical timescales. That does not mean tonight, tomorrow or next Tuesday. It means sometime perhaps within the next 100,000 years or so, give or take enough uncertainty to keep headlines irresponsible. Humans hear soon very differently than stars do. Still, it reminds us that known candidates exist. We are not waiting for impossibilities. We are waiting for timing. And timing in the cosmos is not built around human attention spans. Imagine watching a forest for falling trees, but only for a few minutes each century. If none fall while you watch, it does not mean forests have changed. It means observation windows are short. Modern civilization has had telescopes for only a tiny slice of galactic history, electronic detectors for an even smaller slice, continuous all-sky monitoring for less still. We are newcomers with good instruments. That helps, but it does not entitle us to immediate fireworks. There is also a psychological effect here. Because stars seem fixed overhead, we underestimate how active stellar evolution truly is. Yet stars are changing constantly. Fusion alters cores every second. Winds carry away mass. Pulsations move outer layers. Orbits shift. Magnetic cycles wax and wane. The drama is real. It is simply stretched across timescales unlike our own. If a human life were compressed into a single day, many stellar processes would be continents drifting during breakfast. Real movement, wrong clock, and then, once in a while, the long patience ends. A massive core collapses, a white dwarf ignites, a star crosses a threshold from equilibrium to catastrophe. For a brief period, one point in the galaxy becomes brighter than imagination expects. That flash is the visible punctuation mark at the end of an enormous sentence. Understanding this life story helps answer our broader mystery. Supernovae are not random fireworks scattered evenly in time and place. They arise from specific stars with specific masses, histories, companions, and environments. Some regions of the Milky Way produce more candidates than others. Some eras are busier than others. Some explosions are hidden from us. Now we arrive at an important clarification, because when astronomers use the word supernova, they are not describing one single mechanism. The night sky does not keep only one recipe for stellar catastrophe. It has at least two major ways to produce these brilliant endings, and each tells a different story about what kind of star was there before the blast. That matters for our larger mystery. If we want to understand why we have not clearly seen a recent supernova in the Milky Way, we need to know what kinds of stars can explode, where they tend to live, how often they appear, and what signals they leave behind. A galaxy may seem quiet in visible light, while several different forms of stellar trouble are unfolding in places we cannot easily watch. So tonight, let us separate the two great families of supernovae. One dies because gravity wins. The other dies because pressure wins too suddenly. Both are spectacular. Both reshape space around them. Both can briefly rival the light of galaxies, yet they begin from very different lives. The first major category is the core collapse supernova. This is the dramatic ending of a massive star, the kind of star born with many times the mass of our Sun. Massive stars live fast. Their cores run hot. Fusion races along at a furious pace compared with smaller stars. They burn through hydrogen, then helium, and later heavier fuels in a sequence of shorter and shorter stages. For millions of years, gravity pushes inward while fusion pushes outward. That balances everything. As long as the core can generate enough pressure, the star remains standing. But eventually the central furnace builds up iron. Iron is awkward in stellar economics. Fusing lighter elements up to iron can release energy. Trying to go beyond iron under these conditions does not help support the star. It costs energy instead. That means the star reaches a point where its core can no longer bargain effectively with gravity. And gravity, as always, has been waiting. Once support fails, the core collapses with astonishing speed. In less than a second, the inner regions plunge inward. Temperatures surge. Densities become extreme. Electrons are crushed into protons, forming neutrons and releasing floods of neutrinos. The collapsing core rebounds against itself, launching a shock wave. If that shock is revived strongly enough, the outer layers of the star are blasted into space. What we then observe is a core collapse supernova. The star may leave behind a neutron star, an object so dense that ordinary language starts to lose traction. Or, if the remaining core is massive enough, collapse may continue into a black hole. This route belongs to stars that begin large and live briefly. They tend to be found in regions where stars are still forming, because massive stars do not wander far from their birthplaces before dying. They simply do not live long enough. So when astronomers see a core collapse supernova in another galaxy, they often look towards spiral arms, bright star-forming regions, and places rich in gas and young stellar populations. These explosions are the deaths of cosmic sprinters. They burn bright. They finish early. They leave a mess. There are several subtypes within this family, identified by spectra and details of what material remains in the outer layers. Some retain hydrogen signatures. Some have lost much of their outer envelopes before exploding. Some may have been stripped by strong stellar winds or by close binary companions. Astronomers label these as Type 2, Type 1b, Type 1c, and related categories. The naming system is practical rather than poetic, which is typical of science. If left entirely to branding departments, they would probably be called things like Stellar Thunder Max or Collapse Plus. Still, the labels matter because they reveal what the star looked like before it died. A type 2 event usually shows hydrogen in the spectrum, meaning the outer hydrogen layers were still present. A type 1b lacks hydrogen but shows helium. A type 1c lacks both clear hydrogen and helium signatures, suggesting the star had already shed much of its outer material. Different appearances, same broad theme. A massive star loses stability and collapses. Now we turn to the second great family, and this one is quieter, right up until it absolutely is not. These are thermonuclear supernovae, most famously type 1a supernovae. Their starting point is usually a white dwarf, the dense remnant of a once ordinary star. White dwarfs are what stars like our Sun eventually become after gentler endings. They are compact, hot, and supported not by fusion, but by quantum mechanical pressure from densely packed electrons. Left alone, a white dwarf can simply cool over immense timescales. But many stars live with companions, and companionship in astronomy can become complicated. If a white dwarf orbits another star closely enough, gas may flow from the companion onto the white dwarf. Slowly, steadily, mass accumulates. Alternatively, two white dwarfs in a binary system may spiral together and merge after radiating energy away through gravitational waves. In either case, the white dwarf may approach a critical mass where internal conditions become unstable. Carbon fusion can ignite under degenerate conditions, meaning pressure no longer responds normally to heating. In everyday systems, heating gas makes it expand and cool somewhat. In a white dwarf, that thermostat is broken, so once fusion begins, it can run away very quickly. A thermonuclear flame races through the star, disrupting much or all of it. The white dwarf is often destroyed completely, leaving no compact remnant like a neutron star. That is the classic Type 1 a supernova. Where the core collapse event is gravity crushing inward first, the Type 1a is fusion racing outward first. One implodes, then explodes. The other detonates from within. Both are terrible days for the star involved. Type 1a supernovae are especially valuable to astronomy because they tend to reach fairly consistent peak brightness. That makes them useful as standard candles, objects whose true luminosity can be estimated. By comparing how bright they appear from Earth, astronomers infer distance. These measurements played a crucial role in discovering that the expansion of the universe is accelerating, leading to the concept of dark energy. So some exploding dead stars helped reveal one of the deepest mysteries in cosmology, quite efficient really. Unlike core collapse events, Type 1 a supernova can occur in older stellar populations. Since white dwarfs come from long-lived smaller stars, these explosions may appear in elliptical galaxies or regions with little current star formation. That means the two major families trace different galactic environments. Core collapse supernovae point toward youth. Type 1, a supernovae can emerge from maturity. One follows massive short-lived stars, the other follows the patient afterlife of smaller ones. This distinction matters when discussing the Milky Way. Our galaxy contains both young star-forming regions and older stellar populations. In principle, both categories of supernova should occur here over time, yet visibility, dust, location and timing affect whether we notice them dramatically. Another point worth clearing up is brightness. People often assume all supernovae are equally luminous. They are not. Peak brightness varies by type, by progenitor conditions, by surrounding material, and by explosion physics. Some are unusually bright, called superluminous supernovae. Others are dimmer or partially obscured. Some rise quickly and fade. Some linger longer. Some interact with dense shells of gas shed earlier, creating additional glow. Nature does not produce neat uniform fireworks displays for our convenience. Then there is what each kind contributes to the galaxy. Core collapse supernovae disperse elements produced during stellar burning and in the explosion itself. They enrich space with oxygen, silicon, magnesium, and many others. Their shockwaves stir nearby gas clouds and can trigger later star formation. Type 1, A supernova are especially important sources of iron group elements. Much of the iron in planets, tools, bridges, blood, and kitchen pans owes something to ancient thermonuclear stellar destruction. So whether gravity wins or runaway fusion wins, the rest of the galaxy often receives useful materials, destructive locally, generous globally. We should also note that astronomers classify supernovae initially by what their spectra show, not by directly watching the hidden mechanism. Light carries fingerprints. Absorption and emission lines reveal hydrogen, helium, silicon, and more. From those clues, researchers infer what likely exploded. That is one of astronomy's quiet triumphs. We cannot usually visit the scene. We read the light instead. Imagine identifying a bakery, a metal shop, and a rainstorm solely by scent drifting through a city. Spectroscopy is that kind of detective work, only more precise and with fewer pastries. There are edge cases too. Some stars erupt violently without fully dying. These are sometimes called supernova imposters. A famous example involves Eta Saarinae, which underwent a giant eruption in the 19th century and became one of the brightest stars in the sky for a time, yet survived. So not every apparent stellar outburst is a true final explosion. Some stars stage dramatic rehearsals. Others commit to the finale. This complicates historical records. Ancient observers who saw a new star could have witnessed a genuine supernova, a nova, or another transient event. Modern tools help us distinguish them better, but the sky has always enjoyed ambiguity. For our central topic, the most important lesson is this. Asking why we have not seen a recent supernova in the Milky Way is not one question, but several. Have no massive young stars nearby undergone core collapse visibly? Have no white dwarfs reached thermonuclear catastrophe in clear view? Have explosions occurred behind dust? Have faint or heavily reddened events gone unnoticed historically? Have we simply been between statistically expected events? All are possible ingredients. The galaxy does not owe us equal representation from every category. It only follows probabilities and physics. There is also something humbling in how these two families reflect different forms of endings. One star lives extravagantly and dies young. Another lives modestly, becomes a remnant, then returns unexpectedly for one last enormous statement. The cosmos allows both impatience and delayed drama. Human biographies sometimes do the same. Modern observatories now watch the sky across many wavelengths, improving our odds of catching either type. Optical telescopes scan nightly. Infrared surveys can peer through dust. X-ray and gamma-ray instruments catch energetic signatures. Neutrino detectors wait for core collapse warnings. Radio arrays track expanding remnants. We are better prepared than any generation before us, yet preparation does not control timing. That remains the galaxy's privilege. Somewhere in the Milky Way, a red supergiant may be nearing its final days on stellar timescales. Somewhere else, a white dwarf may be stealing matter grain by grain from a companion, approaching instability. Somewhere beyond thick dust lanes, processes are unfolding we cannot yet see clearly. Silence overhead can be deceptive. The machinery continues. So now that we know the galaxy has more than one route to produce these immense flashes, the next sensible question becomes practical rather than poetic. Given both massive stars collapsing and white dwarfs detonating, how often should a galaxy like ours actually produce supernovae at all? Across a galaxy as wide and crowded as ours, a supernova should not be a once-in-human history kind of miracle. That is the part that makes the silence so interesting. The Milky Way is not a small, quiet island with a few careful stars tucked politely into the dark. It is a huge rotating city of stars, gas, dust, stellar nurseries, old remnants, white dwarfs, red supergiants, crowded clusters, and hidden regions where new suns are still being made. With so much going on, You might expect the galaxy to give us a grand stellar explosion now and then, perhaps not every weekend, which would be inconvenient for both astronomy and sleep schedules, but at least often enough that modern humans should have had a front row view. Astronomers usually estimate that a galaxy like the Milky Way should produce roughly a few supernovae per century, with many sources often summarising the rate as about 1 every 50 years, although the exact number has uncertainty. ESA's integral observations using radioactive aluminum associated with massive star activity found a current core collapse supernova rate around 1.9 plus or minus 1.1 events per century, which fits the familiar about 1 every 50 years idea. NASA also describes massive star supernovae in the Milky Way as occurring about once every 50 years. Now, that estimate sounds wonderfully tidy. 1 every 50 years. Very neat, very calendar friendly, almost as if the galaxy should be sending a reminder. Hello, your scheduled stellar explosion is due this Thursday at 9:15 p.m. Please bring binoculars. But nature rarely behaves like an appointment book. An average rate is not a promise. It does not mean one explosion must appear every 50 years, evenly spaced, with considerate timing and good visibility. It means that if you watched long enough, across enough centuries, and counted enough events, you might find that the typical rhythm works out to something in that range. This is where the mystery becomes less like a contradiction, and more like a probability problem wearing a dark cloak. If the average is around 2 per century, then going many decades without a bright visible supernova is not impossible. It may feel suspicious to us because human memory compresses time. A century feels enormous. But for the Milky Way, a century is barely a pause between breaths. The galaxy has been forming stars for billions of years. Its spiral arms have turned slowly, its gas clouds have gathered and scattered. Its massive stars have lived brief, intense lives and collapsed in places far from our view. Against that scale, even 400 years is not very long. Still, there is a genuine puzzle here. The last clearly observed naked-eye supernova inside the Milky Way was in 1604, often called Kepler's supernova. Before that came Tycho's supernova in 1572, and earlier still, the famous 1054 event that left behind the Crab Nebula. If the galaxy gives us around 2 supernovae per century, then since 1604 we might naively expect several. Not one, not maybe one, several. And yet none has appeared as a bright new star in the sky for everyone to see. That mismatch is exactly why this question keeps returning. The first answer is that should have occurred and should have been seen by human eyes are not the same thing. The Milky Way is full of dust, not household dust, thankfully. No one needs to vacuum Sagittarius. This is interstellar dust, made of tiny grains of carbon, silicates, ice-coated particles, and other materials spread through the galactic disk. It is thin by earthly standards, but across thousands of light years, even thin dust becomes an effective curtain. Visible light can be absorbed and scattered before it reaches us. A supernova on the far side of the galaxy might be bright in its own neighbourhood, but heavily dimmed from Earth. This is one reason we can look at other galaxies and sometimes see supernovae more easily than we can see our own. That sounds backwards at first. Surely our own galaxy should be easier. It is our home after all. But we live inside the Milky Way's disk, looking through its crowded plain. It's like trying to understand a forest while standing among the trees at night, with fog between the trunks and several branches politely poking you in the face. When we observe an external galaxy, we often see its whole structure from outside. The bright explosion can stand out against the galaxy's light. From inside our own, a supernova can hide behind dust lanes, dense star fields, and the complicated, glowing clutter of the galactic centre. Another important point is that different types of supernovae occur in different places. Core collapse supernovae come from massive stars, and massive stars live short lives. Because they die young, they are usually found near star-forming regions, especially along spiral arms. Those regions are often dusty. Star-forming clouds are rich in gas and dust, because that is the material stars form from in the first place. So the very places where massive star supernovae are most likely are also places where visible light may be blocked. That is a rather inconvenient arrangement. It is like the galaxy keeps its fireworks in a cupboard. Type 1a supernova, the thermonuclear explosions of white dwarfs, can occur in older stellar populations and may not be as strongly tied to dusty star-forming regions. But they are less frequent than all core collapse events combined, and their progenitors are harder to identify before explosion. A white dwarf in a binary system may look quite ordinary until the system crosses the threshold into catastrophe. So even though Type 1a supernovae are bright and useful for measuring cosmic distances, predicting one inside the Milky Way is not simple. The galaxy is not handing us a list of white dwarfs with little warning labels saying, "May detonate after breakfast." When astronomers estimate the Milky Way's supernova rate, they do not simply sit under the sky and count explosions. That would be a peaceful but not very efficient career strategy. Instead, they use several lines of evidence. They compare the Milky Way to other similar galaxies. They study the number of massive stars being born. They examine supernova remnants, the expanding leftovers of old explosions. They look at radioactive isotopes, such as aluminum-26, whose gamma-ray emission can trace recent massive star nucleosynthesis and help infer how often massive stars have been exploding. ESA's integral mission used this kind of gamma-ray information to support a core collapse rate close to 2 per century. Each method has uncertainties. Counting supernova remnants is difficult because remnants fade, expand, merge with surrounding gas, or hide in confusing regions. Comparing galaxies is useful, but no two galaxies are perfectly identical. Star formation rates vary. Dust distributions vary, stellar populations vary. Radioactive isotope measurements depend on assumptions about how much material massive stars produce and how it spreads through the galaxy. The result is not a single perfect number. It is a range, a well-informed estimate, a scientific probably around here, which is much better than guessing, but still not the same as knowing every event. So when we say the Milky Way should have one supernova about every 50 years, we should hear that as a broad expectation, not a stopwatch. There is also the problem of clustering in time. Random events do not always look evenly random to human eyes. If you flip a coin 100 times, you may get streaks of heads or tails. That does not mean the coin is broken. It means randomness naturally produces clumps and gaps. Supernovae in the Milky Way may behave similarly. Several might occur in a few centuries, followed by a quieter stretch. Or several might occur but be hidden. The gap since 1604 feels long, but when dust and detectability are included, it becomes less shocking. Historical records also remind us that visibility depends on human circumstances. A supernova must be in the right part of the sky. It must be bright enough. It must not be too close to the sun's apparent position when it peaks. It must occur during a period when people are watching, recording, preserving, and later interpreting observations accurately. Clouds, seasons, geography, war, culture, and simple human distraction all matter. There may have been events that were noticed by some and not widely recorded, or recorded in ways that are now difficult to interpret. The sky may be reliable, but archives are human, and humans occasionally misplace things, including entire centuries of useful notes. Modern astronomy improves our chances enormously, but it has only been modern for a short time. Sensitive all-sky surveys, neutrino detectors, space telescopes, infrared observatories, radio arrays, and automated transient searches are recent tools compared with the timescale of supernova rates. We have had truly powerful, multi-wavelength monitoring for only a tiny fraction of the interval since Kepler's supernova. If a galactic supernova happens now, especially a core collapse event, it would be very difficult for science to miss completely. Even if dust hid the visible flash, neutrino detectors could catch the burst, infrared telescopes might see through the dust, and radio or X-ray observatories could find the aftermath. But in earlier centuries, a hidden event could pass with much less notice. In fact, astronomers have found evidence for relatively recent supernova remnants in the Milky Way that were not widely observed as bright historical events. One famous candidate is G 1.9 plus 0.3, often described as the youngest known supernova remnant in our galaxy, with the explosion likely occurring around the late 19th century or early 20th century as seen from Earth, but hidden by dust near the galactic centre. Its existence is a reminder that the Milky Way may have produced supernovae without giving ordinary human eyes anything obvious to see. The silence in the sky may partly be an illusion created by interstellar curtains. This changes the emotional shape of the question. Instead of asking, why has nothing happened? We begin asking, what happened where we could not see it? That is a very different kind of mystery. Less like waiting for a doorbell that never rings, more like learning that someone has been knocking on the far side of a very thick wall. The rate also depends on what we include. Core collapse supernovae alone may happen roughly once or twice per century. Type 1a events add to the total but at a lower rate. Together, broad estimates often place the Milky Way's total supernova rate somewhere around 2 or 3 per century, though the uncertainty is meaningful. That means our galaxy should be producing these events over human historical timescales, but not so often that any individual lifetime is guaranteed a spectacular naked-eye display. This is a useful distinction. If you are born during a quiet interval, you could live a long life and never see a Milky Way supernova. That would not prove the rate wrong. It would only prove that cosmic timing does not care about personal schedules. A person might live between rare storms. A village might go decades without a flood. A forest might stand calm for a century before fire returns. Nature has rhythms, but not all rhythms are conveniently regular. There is another subtlety. A supernova rate for the whole Milky Way includes regions we barely see. The galaxy is not a small circle around the Sun. We are located in one part of the disk, about halfway out from the centre. Much of the star-forming action lies toward the inner galaxy, where dust and stellar crowding make observation harder. If supernovae occur there, they belong to our galaxy, but they may not belong to our sky in the obvious visual sense. Imagine someone saying there are concerts every week in your city, but most are underground, far away, behind locked doors, and performed in frequencies only bats can hear. Technically lively, personally hard to enjoy. That is a little like living inside the Milky Way. The expected rate also connects to star formation. Massive stars are the raw material for core collapse supernova. If a galaxy forms many massive stars, it will eventually produce more core collapse explosions. Starburst galaxies, where star formation is intense, can host supernova more often. Quieter galaxies produce fewer. The Milky Way is active but not extreme. It forms stars steadily, but it is not currently undergoing a wild starburst phase, so our supernova rate is moderate, enough to matter, not enough to be constant. This helps explain why we see supernovae regularly in other galaxies. Astronomers monitor huge numbers of galaxies. Even if any one galaxy produces only a few supernovae per century, watching thousands or millions of galaxies gives many chances. It is the difference between waiting for one person to have a birthday and watching an entire city. Somewhere, candles are being lit. For the Milky Way alone, we are waiting on one galaxy's schedule, and that schedule is slow. There is also observational selection. Bright extragalactic supernovae are often found because they appear as new points of light against a known galaxy. Automated surveys compare new images to old ones and flag changes. In our own galaxy, the background is complicated. Stars overlap. Variable stars brighten and fade. Dust reddens light. Crowded fields make detection difficult. A galactic supernova would likely become very obvious if nearby and unobscured, but a distant dusty event near the centre could be more subtle than people imagine. This is where infrared astronomy becomes essential. Infrared light passes through dust more effectively than visible light. A hidden supernova may glow in infrared, even if optical telescopes struggle. Radio observations can also reveal expanding shock waves. X-rays can trace hot gas and compact remnants. Gamma rays can reveal radioactive decay. Neutrinos, as we mentioned earlier, can escape from the heart of a core collapse before light fully breaks out. Modern astronomy is no longer dependent on whether the night sky looks dramatic to our eyes. That is reassuring, because our eyes are lovely but limited. They are good for sunsets, cats, and locating snacks. They are not enough for a dusty galactic disk. So, how often should the Milky Way have supernovae? The best gentle answer is often enough that several should occur in a few centuries, but not so often that we should expect one to be plainly visible from Earth every generation. A broad working figure is around 2 per century, perhaps one every 50 years, with uncertainty and with many events potentially hidden from visible view. That makes the absence of a recent naked eye event interesting, but not impossible. It suggests concealment, timing, and observational limits more than a truly silent galaxy. And this is where the story becomes especially satisfying. The Milky Way may not be failing to produce supernovae. We may simply be living in a place where the galaxy's architecture hides many of its biggest moments. Dust, distance, direction, and randomness all conspire to make a dramatic event look like nothing at all. There is something quietly humbling about that. We often assume the most important events should be obvious. A star explodes, surely everyone should see it. But the universe does not always perform on the visible stage. Sometimes enormous things happen behind curtains. Sometimes the evidence arrives later, in expanding shells of gas, radioactive traces, or faint signals gathered by instruments that did not exist when the light first passed Earth. So the apparent calm above us may be misleading. The Milky Way's expected supernova rate tells us that explosions should be happening across cosmic time. The historical gap tells us we have not seen a bright one recently. The dust and structure of the galaxy tell us why that may not be surprising, and the remnants scattered through space tell us the story is not over, nor was it ever truly quiet. From here, the question naturally narrows. If the numbers say the galaxy should be producing supernovae, then what exactly has kept them from appearing clearly in our sky? Something about an empty stage makes people curious. If we know an event should happen now and then, and the lights remain low for centuries, we start to suspect a hidden reason. That is exactly where we now stand with supernovae in the Milky Way. By broad astronomical estimates, our galaxy should produce a few supernovae every century or so, not clockwork, not guaranteed on a tidy schedule, but often enough that modern observers naturally ask why the sky has not delivered a bright, obvious, unforgettable example in recent generations. We know stars capable of exploding exist. We know past explosions happened. We know other galaxies continue to produce them. And yet, overhead, no great new star has suddenly appeared to dominate the night in the way ancient skywatchers once recorded. So where is everyone's dramatic stellar finale? The first answer is deceptively simple. Recent does not mean what we think it means. For human beings, 400 years feels like a very long time. It spans empires, revolutions, industrialization, electricity, flight, radio, computers, the internet, and the curious invention of arguing publicly with strangers at all hours. It is a substantial stretch of history. For a galaxy, it is almost nothing. The Milky Way is more than 10 billion years old. Massive stars are born and die within millions of years. Spiral arms rotate slowly over hundreds of millions. Gas clouds drift, collapse, disperse, and reform over enormous timescales. Against that backdrop, 4 centuries is barely enough time for the galaxy to notice we have arrived. This difference in timescale can distort intuition. We hear a few per century and imagine reliable pacing, but averages do not create regular spacing. If a forest averages several lightning strikes each summer, some years may feel busy, others quiet. If buses arrive every 10 minutes on average, you may still wait 25 in the rain while reconsidering optimism. Nature allows clusters and gaps. Supernovae almost certainly do the same, so one reason for the silence is statistical patience. A dry spell is possible even if the long-term rate remains normal, but statistics alone are not the whole story. The second reason is that the galaxy is not transparent. This may be the single most important practical answer. Between us and much of the Milky Way lies interstellar dust, a thin but widespread mixture of microscopic grains made from carbon compounds, silicates, ices, and other materials. In a room, dust is mildly annoying. Across thousands of light years, dust becomes an optical strategy. It blocks visible light. Not perfectly, but effectively enough. A supernova can explode brilliantly behind thick dust lanes and appear far dimmer to human eyes, perhaps dim enough to escape widespread notice. This is especially relevant toward the galactic centre, where dust, gas, and crowded star fields combine into one of astronomy's great visual traffic jams. We happen to live inside the disk of the galaxy rather than above it. That means we often look sideways through long stretches of cluttered material. Imagine trying to observe fireworks from inside a foggy forest. That is a closer analogy than many realise. Ironically, astronomers sometimes detect supernovae in distant galaxies more easily than those in our own. When we observe another galaxy from outside, its structure can be seen at once. A new bright point stands out, but inside our own galaxy, distance, dust, and overlapping stars complicate the view. Living within the Milky Way is beautiful. It is also observationally inconvenient. The third reason is location. Not every supernova occurs in a friendly part of the sky. If one erupts far across the galaxy, low on a horizon from many populated regions, near the dense star fields of the galactic centre, or in a season when it is poorly placed, fewer people may notice it directly. Historically, this mattered greatly. Ancient and early modern observers did not have automated surveys scanning the entire sky every clear night. They had eyes, discipline, patience, records, and weather problems. A bright event could still be missed locally, seen only in some regions, or poorly preserved in surviving documents. Even now, visibility depends on timing. If a transient brightens near the apparent direction of the sun, daytime glare can hide it during crucial weeks. If clouds dominate a season across large regions, attention fades. If it rises where urban light pollution has washed out much of the sky, many casual observers simply never notice. The heavens are still there. Human habits changed. That is the fourth reason. For most of history, many people knew the night sky personally. Farmers, navigators, travellers, scholars, shepherds, sailors, and city dwellers without electric lighting saw stars regularly. Familiarity with constellations was common practical knowledge. Today, many millions live under bright urban skies where only the brightest stars are obvious. Entire generations may know constellations mostly from apps rather than repeated observation. This is not criticism, it is infrastructure. But it means the threshold for someone notices immediately has changed. A new bright star would absolutely attract attention if dramatic enough. Yet modest events in complex sky regions could take longer to become culturally visible than we assume. The fifth reason is that some supernovae may have happened recently enough in astronomical terms, but not obviously in visible light. A famous example often discussed is G1.9 plus 0.3, regarded as the youngest known supernova remnant in the Milky Way. Its explosion likely occurred around the late 19th or early 20th century as seen from Earth. Yet, It was not widely observed because it lies near the galactic centre behind heavy obscuration. That possibility changes everything. The silence may not be silence. It may be concealment. Think about how often humans mistake I did not witness it, for it did not happen. Astronomy repeatedly corrects that instinct. Planets existed before telescopes. Galaxies existed before we recognized them. Black holes existed before we named them. Supernovae may have occurred while hidden from ordinary sight. The sixth reason involves what counts as seen. Do we mean naked eye visible? Photographed? Detected in infrared? Reconstructed later from a remnant? In the past, seen usually meant noticed in the sky by humans directly. Today, detection can happen through many channels. Infrared light penetrates dust better than visible light. Radio telescopes trace expanding remnants. X-ray observatories reveal hot-shocked gas. Gamma rays can expose radioactive decay products. Neutrino detectors may catch core collapse signals even before light emerges fully. If a galactic supernova happened tomorrow behind thick dust, modern science might still know quickly, even if many people never saw a blazing star overhead. That is a remarkable shift. The sky can whisper now, and we have better ears. The seventh reason is that progenitor stars are not evenly distributed. Core collapse supernovae come from massive stars, and massive stars die young. They remain near star-forming regions, especially spiral arms rich in gas and dust. Those same regions are among the hardest to observe clearly in visible light, so the stars most likely to explode are often placed exactly where explosions are easiest to hide. This feels almost theatrical. The galaxy stores its loudest performers backstage. Type 1A supernovae, involving white dwarfs in binary systems, can occur in older stellar populations and may appear in cleaner regions, but they are less predictable individually and not constant in timing. A white dwarf may spend ages quietly accreting mass, or spiralling toward merger before crossing the threshold into catastrophe. Again, no appointments, only probabilities. The eighth reason is expectation itself. Modern media has trained many people to imagine major celestial events as globally obvious spectacles. We expect instant headlines, live streams, dramatic images, and universal awareness. Yet astronomical events vary greatly in how photogenic they are from Earth. Some are subtle scientifically but profound physically. Some are loud visually but modest scientifically. Some become famous because cameras were ready. Others become famous later because data was. If a supernova occurred in a dusty region and first announced itself through a neutrino burst, that would be one of the biggest scientific moments of the century, even if the average person only heard, "Scientists detected something interesting in space." Not every revolution glows visibly. The ninth reason is randomness layered atop complexity. Suppose the Milky Way averages 2 supernovae per century. Some may be hidden, some may occur where geometry is poor, some may be dimmer than expected, some may peak during solar conjunction, some may be reconstructed only later. Now add centuries. The chance of a noticeable gap grows less mysterious. This is where many cosmic puzzles soften. What first looks impossible often becomes understandable when multiple moderate factors overlap. No single cause, many small ones. That is often how reality works. There is also a psychological component to silence. Humans dislike waiting without feedback. If we know something should happen eventually, the lack of visible progress can feel meaningful, but stars nearing explosion do not issue status updates. Betelgeuse dimmed notably in 2019 to 2020 and inspired worldwide excitement that perhaps a supernova was near. Instead, the leading explanation involves surface changes and dust, not imminent collapse. The star reminded us of an important lesson. Interesting does not always mean immediate, and immediate in stellar language may still mean later than our grandchildren prefer. There is a charming humility in all this. We built telescopes, equations, observatories, satellites, detectors under mountains, and instruments colder than deep space itself. We became exquisitely capable watchers, yet the galaxy can still say, "Not now," or "behind that dust cloud," or "You'll understand this better in radio wavelengths." Science advances anyway, sometimes through spectacle, sometimes through patience. So why haven't we seen one recently? Because recently is short, because averages are not schedules, because dust hides light, because we live inside the disk, because star-forming regions are messy, because some events may already have happened unseen, because detection no longer means only eyesight, because the universe is under no obligation to entertain us on demand, and perhaps because waiting sharpens appreciation. If a clear Milky Way supernova appeared tonight, it would not merely be bright, it would feel historic precisely because of this long quiet interval. People across Earth would step outside, scientists would redirect every suitable instrument, newsrooms would become temporarily interested in stellar evolution, social media would contain both wonder and at least one claim that it was definitely weather balloons. The gap gives future spectacle weight. Stand beneath a clear rural sky, and the Milky Way can look like a pale river of light crossing the darkness. It appears open, exposed, almost generous. We see a bright band overhead and instinctively assume we are looking straight into the heart of our galaxy. We are not. What we are really seeing is filtered light, partial information, and a scene with enormous sections concealed behind material too thin to notice nearby, yet powerful enough to hide entire stellar populations across long distances. This brings us to one of the most important answers in our search for missing supernovae. Yes, the galaxy may very well be hiding them from us, and the chief accomplice is dust. Not household dust, thankfully. No forgotten shelf in the universe has become this influential. Interstellar dust consists of tiny solid grains floating between stars. Many are smaller than smoke particles. They are made of silicates, carbon-rich compounds, frozen coatings, and debris from previous generations of stars. Individually, each grain is insignificant. Collectively, spread through clouds and lanes across tens of thousands of light years, they become a veil. This veil does something simple and profound. It blocks light. More specifically, it scatters and absorbs certain wavelengths of light, especially visible light. Blue wavelengths are affected strongly, red somewhat less, infrared less still. So when starlight crosses dusty regions, it can dim, redden, distort, or vanish from ordinary view. That means an object can be bright in reality and faint to us. This happens constantly. It is one of astronomy's favourite ways to humble assumptions. If a star exploded as a supernova on the far side of the Milky Way, especially toward the galactic centre, the blast might be intrinsically brilliant. It could outshine billions of suns for a short period. Yet by the time its visible light fought through thick lanes of dust and gas, much of that brilliance could be reduced or hidden. So when we ask why we have not seen many recent supernovae with our eyes, dust is not a side note. Dust is central. To understand why, we need to understand where we live. Our sun sits in the disk of the galaxy, not at the centre and not above the plane. We orbit in one of the spiral arm regions, roughly halfway out from the galactic core. This gives us a beautiful inside view, but it also means that when we look toward the centre, we are peering through immense stretches of crowded galactic disk. Imagine standing in a dense forest and trying to observe the farthest tree trunk through fog, branches, leaves, insects, drifting smoke, and several rude bushes. That is closer to our galactic centre view than many people realise. The centre of the Milky Way lies in the direction of the constellation Sagittarius. It is one of the richest, busiest, most fascinating regions in the sky. It contains dense star fields, giant molecular clouds, magnetic structures, energetic remnants, clusters, and at the very core, the supermassive black hole known as Sagittarius A star. Yet in visible light, much of that central grandeur is obscured. If human eyes were our only tool, we would know far less about our own galactic centre than about some distant galaxies. That sounds absurd. It is also true. This is because visible light struggles through dusty regions. Some lines of sight toward the centre suffer enormous extinction, meaning light is dimmed by many magnitudes. A star that would otherwise blaze clearly can become nearly invisible. A supernova that should command the sky may instead become a muted or entirely hidden event. The galaxy, in effect, has curtains, and it drew many of them across the stage where some of the most interesting activity occurs. Dust does not distribute itself evenly. It gathers in clouds, lanes, filaments, and star-forming regions. Some directions are relatively clear, others are heavily blocked. This patchiness creates a sky full of uneven transparency. In one direction you may see deep into the disk. In another, your view ends much sooner. Astronomers call some clearer windows toward the bulge Baird's window, and similar regions, places where lower extinction lets us peer more effectively into the inner galaxy. Even our access points need names because they are so useful. Now consider supernovae. Massive stars, the ones that produce core collapse supernovae, tend to be born in active star-forming regions. Those regions are rich in gas and dust because stars form from collapsing clouds of that material. So the very stars most likely to explode dramatically often spend their short lives in messy neighbourhoods. Then they die there. This is observationally unfortunate. It is as if fireworks factories were legally required to operate inside thick fog banks. Many likely supernova sites in the inner galaxy combine three challenges at once: distance, crowding, dust. Distance weakens apparent brightness. Crowding makes objects harder to distinguish against rich backgrounds. Dust removes visible light. Together they can turn obvious events into subtle ones. This helps explain a puzzle people often have. Why do astronomers discover supernovae in distant galaxies regularly, yet seem to wait so long for one in our own? Because with another galaxy, we often get an outside view. A bright new point appears against a known shape. Automated surveys compare images and flag changes. The geometry is clean. Inside our own galaxy, we are embedded in the clutter. It is the difference between seeing a lighthouse from offshore and trying to locate a lamp while standing inside a crowded warehouse. Both contain light. Only one is convenient. History gives us hints that hidden supernovae are real possibilities. The youngest known supernova remnant in the Milky Way is often identified as G 1.9 plus 0.3. Its explosion likely occurred only a century or two ago as seen from Earth. Yet no famous worldwide record describes a brilliant new star. Why not? Why? Heavy extinction near the galactic centre is the leading suspect. Something happened. The sky simply did not present it clearly to unaided eyes. That possibility should permanently change how we hear the phrase, "We haven't seen one." Seen in visible light by many people is a narrow category. The galaxy has more options. Fortunately, astronomers are stubborn. When visible light fails, we use other wavelengths. Infrared astronomy is especially valuable because infrared light penetrates dust far better than visible light. Regions opaque to ordinary telescopes can become crowded and vivid in infrared surveys. Hidden stars emerge, structures appear, central clusters reveal themselves. Many of the most striking modern images of the galactic centre come from infrared observations precisely because visible light cannot do the job. Radio astronomy goes further in different ways. Radio waves can pass through dust with little trouble. Radio telescopes map gas clouds, magnetic fields, pulsars, supernova remnants, and the dynamic environment around Sagittarius A star. X-rays reveal hot energetic gas, compact remnants, and violent processes. Gamma rays trace extreme phenomena and radioactive signatures. Neutrino detectors wait for bursts from collapsing stellar cores. In other words, when curtains close in one wavelength, science walks around the theatre. This multi-wavelength approach has transformed our understanding of the inner Milky Way. We now know the centre is not dark or empty. It is active, crowded, chemically rich, and historically eventful. The darkness was ours, not the galaxy's. There is another subtle trick dust plays. It reddens light. Because shorter wavelengths scatter more efficiently, surviving visible light from distant stars appears redder than it truly is. This is called reddening. A star behind dust may look cooler or dimmer than it intrinsically is unless corrected carefully. So dust not only hides, it edits, it changes appearances. This means estimating how bright a hidden supernova would have looked becomes a detective exercise. Astronomers reconstruct extinction along the line of sight, model intrinsic luminosity, compare remnants, and infer what human observers might have seen under clearer conditions. Sometimes the answer is startling. An event that might have rivaled planets in brightness could have been reduced to something modest or nearly invisible. The curtain need not be perfect to be effective. Then there is the galactic bulge, the dense central swelling of stars surrounding the nucleus. Even without dust, this region is crowded. Countless stars overlap in our line of sight. Finding one changing object against such a background can be difficult, especially before modern digital monitoring. Imagine spotting a single blinking window in a city skyline from far away during haze. Now do it with 17th century equipment. The fact that ancient observers saw any transient events at all is impressive. Modern city lighting adds another layer. If a somewhat obscured supernova rose over many populated areas today, casual observers under bright skies might never notice. Professional surveys would likely catch it, but public cultural awareness could lag behind expectations. People often imagine that a galactic supernova must automatically become the brightest thing in the night sky. Some would, some might not. Location and extinction matter enormously. Suppose a core collapse supernova occurred near the centre, intrinsically brilliant but behind dozens of magnitudes of visual extinction. It could be scientifically revolutionary and visually disappointing. Astronomers would be ecstatic. Neighbours might ask why anyone is excited about that faint reddish thing near the horizon. Both reactions could be reasonable. Dust also connects to starbirth. Giant molecular clouds contain both gas and dust. They are the nurseries of massive stars. Those stars live only millions of years, then explode nearby. This means many core collapse supernovae occur before stellar winds and radiation have fully cleared their surroundings. The star dies close to where it was born. Birthplace and burial ground can be adjacent. Again, not poetic, just efficient. There is something deeply instructive here about perspective. Humans tend to think that if something important happens, it should be obvious from where we stand. But where we stand is inside a dusty spiral galaxy, halfway out, looking through crowded lanes with eyes tuned to one small slice of the electromagnetic spectrum. That is not a neutral viewpoint. It is a limited seat in a complicated auditorium. Science progresses by admitting that. Once we expanded beyond visible light, whole hidden populations appeared. Embedded newborn stars, obscured clusters, dark clouds glowing in infrared, energetic remnants in X-rays, radio arcs, central dynamics around Sagittarius A star. The Milky Way did not become more interesting. We became better at seeing it. So, is the galaxy hiding supernovae from us? Quite possibly yes. Not maliciously, not intentionally, simply through structure, material, and geometry. Dust grains formed from old stars drift through the disk. Clouds gather. Light is filtered. Observers inside the system inherit blind spots. The result is that some of the most dramatic events in our own galaxy may occur without the sky offering a bright naked eye announcement. That can feel disappointing until you realise something better. It means there may have been more supernovae than we thought. The galaxy may be busier, louder, and more alive than visible history suggests. Long before radio telescopes, space observatories, digital sky surveys, or scientists receiving alerts on glowing screens at 3 in the morning, people still watched the heavens carefully. In some ways, they watched more carefully than many of us do now. The night sky was calendar, compass, clock, storybook, omen, and entertainment all at once. If something changed up there, it mattered. And when a bright new star suddenly appeared where no star had been seen before, people noticed. This is one of the most remarkable bridges between ancient observation and modern astrophysics. Human beings, with no CCD cameras, no spectroscopy, no satellites, and no idea what a neutron star was, still recorded some of the most violent stellar deaths in galactic history. They did not call them supernovae. They called them new stars, guest stars, strange stars, temporary lights. But many of those records describe exactly what we now recognise as supernovae. So when we ask why we have not seen one recently in the Milky Way, it helps to remember that humans absolutely have seen them before. Our ancestors looked up, noticed the sky behaving strangely, and wrote it down. That is a rather beautiful thought. Across centuries, languages, empires and cultures, people separated by geography were all looking at the same galaxy. The first famous historical candidate often discussed is the event of 185 CE. Chinese astronomers recorded what they called a guest star, visible for many months. Many researchers associate this with the supernova remnant CW86, though details remain debated. Even the uncertainty is interesting. It reminds us that reconstructing ancient astronomy is detective work. Records may be brief, coordinates may use old sky divisions, descriptions can be poetic, practical, or frustratingly vague. Historians and astronomers work together, comparing texts, dates, visibility, and modern remnants. Sometimes the evidence fits neatly. Sometimes the universe shrugs and leaves partial notes. Still, the 185 event appears to represent an early clear case of humans noticing something extraordinary in the sky and preserving the memory. Then comes one of the most celebrated stellar appearances in recorded history, the supernova of 1006. This event, known today as SN 1006, may have been the brightest stellar event in recorded human history. Observers across Middle East, China, Japan and Europe described a brilliant new star visible for months. Accounts suggest it was bright enough to cast shadows and remain visible in twilight under some conditions. Imagine stepping outside at night and seeing a star so luminous it feels misplaced, almost like a planet where no planet belongs. Modern astronomy links this to the remnant associated with SN 1006, located about 7,000 light-years away. That distance is enormous, yet the explosion was so powerful that medieval observers watched it with naked eyes. No telescope, no warning. Just one night the sky had changed. Then there is the event of 1054, among the most famous because its remnant is one of astronomy's treasures. Chinese and other East Asian records describe a guest star appearing in 1054, visible even in daylight for weeks and at night for many months. Today we identify this with the explosion that created the Crab Nebula. At the centre of the Crab Nebula lies the Crab Pulsar, a neutron star spinning rapidly and emitting beams of radiation. In other words, modern instruments can still study the compact corpse of the star whose death people witnessed nearly 1,000 years ago. Think about the continuity there. A person in 1054 looked up and saw a new light. A scientist today points a radio telescope or X-ray observatory at the remnant and studies the aftermath. One event, separated by centuries, connected by curiosity. The 1054 supernova also carries an intriguing historical mystery. Some scholars have debated why European records appear sparse compared with East Asian sources. Cultural context, weather, preservation of documents, political circumstances, and observational traditions all matter. This is an important lesson. The sky may be universal, but records are local. What humanity remembers depends not only on what happened, but who was watching, how they wrote, and whether the paper survived. Next comes the supernova of 1181, another likely historical galactic event recorded in East Asian sources. It remained visible for months. For a long time, identifying its remnant was uncertain, but modern work has increasingly linked it with PA30 and its unusual central star. Again, notice the pattern. Ancient observers provide the date and sky location. Modern astronomy provides the physical explanation. Together they solve puzzles neither era could solve alone. Then we arrive in the age of early modern Europe, where the sky was about to challenge inherited ideas in dramatic fashion. In 1572, a bright new star appeared in the constellation Cassiopeia. It was observed by many, but famously studied by Tycho Brahe. This event is now known as Tycho's supernova. Why did it matter so much? At the time, many scholars influenced by Aristotelian ideas believed the heavens beyond the moon were changeless and perfect. Comets and atmospheric effects were one thing, but a truly new star among the fixed stars challenged that worldview. Tycho carefully measured its position relative to known stars and found no detectable parallax consistent with something nearby in the atmosphere. The object was distant among the stars themselves. The heavens changed. That conclusion was revolutionary. Sometimes a supernova does more than destroy a star. Sometimes it helps destroy an outdated philosophy. Tycho's records became a milestone in the scientific transition toward a more dynamic cosmos, and the remnant of that explosion still exists today, studied in radio, optical, and X-ray wavelengths. Then came 1604, the last clearly observed naked-eye supernova in the Milky Way. This event is often called Kepler's supernova because Johannes Kepler observed and described it, though many others saw it as well. Appearing in the constellation Ophiuchus, it became bright enough to attract wide attention. Kepler studied it intensely. The timing was symbolic. Astronomy was changing rapidly. Copernican ideas circulated. Telescopes were about to transform observation. Mathematics was gaining power, and overhead, a star exploded. If the universe enjoys dramatic timing, it was showing off. Kepler's supernova remains the last widely accepted naked-eye supernova seen in our galaxy. Since then, centuries have passed without an equally obvious successor. That gap is the heart of our broader mystery. Because humans used to see these events occasionally, then apparently stopped. Or more precisely, obvious visible events stopped. This is where historical records become especially valuable. They remind us that supernovae are not hypothetical in the Milky Way. They happened often enough to enter chronicles repeatedly across many centuries. They also reveal something about observation itself. People once knew the sky well enough to detect change quickly. A new star was meaningful because the ordinary sky was familiar. Today many people live under light pollution severe enough that even the Milky Way band is invisible. If Tycho's supernova occurred in a modestly obscured region, over many modern cities some residents might miss it entirely until social media informed them that the cosmos was trending. Progress comes with trade-offs. We gained satellites. We lost some darkness. There is another charming aspect to these historical events. Nobody watching them knew the full cause. Observers described brightness, colour, duration, and position. They debated meaning. Some saw omens, some saw divine signs, some saw natural phenomena. None knew they were witnessing shock waves, nucleosynthesis, collapsing cores, or thermonuclear runaways. Yet their raw observations were still scientifically precious. This is worth remembering in any age. You do not need perfect theory to collect valuable facts. Sometimes careful noticing comes first. Understanding arrives later. Modern researchers use those ancient records in surprisingly practical ways. Dates constrain remnant ages. Brightness descriptions help estimate explosion type. Reported positions narrow remnant identifications. Duration of visibility informs models of luminosity and extinction. A monk's note. A court astronomer's log. A scholar's careful measurements. All can become data centuries later. Human memory, when written down, can outlive empires and assist astrophysics. There are also likely events we did not preserve clearly. Wars destroy archives, fires consume manuscripts, languages vanish. Local traditions go unrecorded in globally dominant histories. Some supernovae may have been noticed by communities whose records did not survive or were never centralized. So the list of historical supernovae is almost certainly incomplete. What we have is not every performance. It is the surviving ticket stubs. This should make us cautious when saying none occurred. Sometimes we mean only none are clearly documented in sources we still possess. Still, the known set is impressive enough. 185 CE, 386 CE, 393 CE, 1006 CE, 1054 CE, 1181 CE, 1572 CE, 1604 CE. Several likely galactic supernovae witnessed by humans directly. Several stellar deaths bright enough to mark history. Several reminders that the Milky Way has never been a static background. Then why the modern quiet? Partly timing, partly dust, partly observational circumstance, partly chance. And perhaps partly because some more recent events occurred where visible light could not reach us cleanly. There is something almost comforting in that. The absence of spectacle does not mean inactivity. It may only mean we occupy a complicated vantage point inside a dusty spiral system. Imagine future historians reading our era's records after the next great supernova appears. They may note centuries of waiting, public fascination, frantic telescope scheduling, endless photographs, conspiracy theories appearing within minutes, and at least one person insisting they saw it first through a kitchen window. Human behaviour changes less than technology. The stars probably know this. What historical supernova also give us is perspective on awe. We sometimes think modern science has replaced wonder. In truth, it has refined it. Ancient observers felt astonishment at new star. We feel astonishment plus spectroscopy. Both are respectable responses. So yes, humans have seen supernovae in the Milky Way before. We have stared at them, named them, feared them, measured them, debated them, and passed their memory forward. Which naturally leads us to the next question. If 1604 was the last clearly seen galactic supernova, what exactly happened in that event, and why has no equally obvious successor stepped onto the sky since then? By the early 17th century, Europe was already changing quickly. Old certainties were under pressure. Navigation had redrawn maps. Printing presses spread arguments efficiently. Mathematics was becoming a language of nature. Telescopes were just about to transform the sky forever. It was, in many ways, an era unusually prepared to notice that the heavens were not fixed. Then, in 1604, a new star appeared. Not a faint curiosity for specialists only. Not something tucked invisibly into a dusty corner. A bright object emerged in the constellation Ophiuchus, near the path of the planets, where attentive observers could hardly ignore it. It shone strongly enough to draw widespread notice and became the last clearly observed naked-eye supernova in the Milky Way. More than 4 centuries later, we still speak of it with a certain reverence, because since then, nothing equally obvious from our own galaxy has replaced it. Today we usually call this event Kepler's supernova, named after Johannes Kepler, who studied it carefully and published observations. Kepler did not cause the supernova, despite what naming conventions sometimes imply. Astronomers simply enjoy honouring people by attaching their names to explosions they had no control over. A sensible tradition, really. Kepler was one of the great scientific minds of the age. He is best known for the laws of planetary motion that described how planets orbit the Sun in ellipses rather than perfect circles. That alone would secure his place in history. Yet while he was transforming celestial mechanics, the sky handed him another puzzle. A bright new star where none had been seen before. For observers of the time, this mattered deeply. Even after earlier events like Tycho's supernova in 1572 had challenged older beliefs, many still carried philosophical assumptions that the heavens were stable and changeless beyond Earth's atmosphere. Temporary lights among the stars were unsettling evidence. The universe once again refused to remain tidy. Historical reports suggest the 1604 star became extremely bright, perhaps rivaling the brightest planets. It was visible for many months, gradually fading over time. To people watching without modern astrophysics, it was a brilliant intruder. To us, it was the death of a star whose light happened to reach Earth during a period when humans were finally learning how to measure the sky with new seriousness. The timing is extraordinary. Had it happened centuries earlier, records might have been less precise. Had it happened centuries later, telescopes and spectroscopy would have transformed the data. Instead, it arrived in a narrow window between worlds. 1 foot in ancient skywatching, 1 foot in modern science. So what actually happened out there? Modern astronomers identify the remnant of the event as Kepler supernova remnant, an expanding shell of gas and debris located thousands of light years away. By studying that remnant in radio, optical, infrared, and X-ray wavelengths, researchers can reconstruct the explosion long after the visible spectacle faded. This is one of astronomy's quieter triumphs. The fireworks ended centuries ago. The evidence remains. At first glance, you might assume the 1604 event came from a massive star collapsing under its own gravity. That is one classic route to supernovae. But evidence now strongly suggests Kepler's supernova was more likely a Type 1a supernova, the thermonuclear destruction of a white dwarf. That means the story began not with a giant youthful star, but with a stellar remnant. Sometime earlier, an ordinary star had lived its life and become a white dwarf, a dense object roughly Earth-sized but containing mass comparable to the Sun. In a binary system, white dwarfs can interact with companions. Matter may be transferred, or 2 white dwarfs may eventually merge. Under the right conditions, enough mass accumulates that carbon fusion ignites catastrophically. No gentle adjustment, no stable thermostat, just runaway thermonuclear burning. The white dwarf is disrupted in a vast explosion. That is the likely mechanism behind the 1604 event. In practical terms, a dead star returned for one final and dramatic statement. There is something wonderfully unreasonable about that. The star retired, then exploded. Researchers have spent years examining the remnant to understand the details. X-ray observations reveal iron and other heavy elements consistent with Type 1a models. The shape of the remnant, however, is somewhat asymmetric and complex, suggesting the exploding star was interacting with surrounding material. This makes Kepler's supernova especially interesting. It is not just a textbook case. It is a reminder that nature likes to personalize events. Some models propose the white dwarf had a companion star losing material into the surrounding region before the explosion. Others examine alternative binary scenarios. The debate over the exact progenitor system has been lively, technical, and probably responsible for several conference coffee refills. What we know with confidence is enough to be impressive. A stellar remnant detonated. Its debris expanded outward at enormous speed. Centuries later, we can still map the aftermath. Imagine finding the ruins of a long-vanished city and reconstructing the politics of its final week. That is roughly the level of ambition astronomers bring to supernova remnants. The remnant itself continues expanding today. Shock waves plough into surrounding gas. heating material to millions of degrees and generating X-rays. Magnetic fields accelerate particles. Filaments glow. The explosion remains dynamically active long after the bright visible phase passed. This is another common misconception worth correcting. A supernova is not one flash and then nothing. The flash is brief. The consequences can last thousands of years. Why was the 1604 event so visible compared with the silence since then? Several factors helped. First, location. It was not hidden behind the worst dust lanes of the galactic centre. Second, intrinsic brightness. Type 1. A supernovae can be extremely luminous. Third, circumstance. Observers in literate societies with growing scientific interest were watching and recording. Those three ingredients do not always align. When they do, history notices. There is also a charming human detail here. In 1604, no one knew about white dwarfs, no one knew nuclear fusion, no one knew relativity, quantum mechanics, neutron stars, or galaxies beyond the Milky Way. Yet they still noticed something important and described it carefully. Science often advances this way. Observation first, explanation later. Kepler himself interpreted the event through the frameworks available to him, blending mathematics, astronomy, and the intellectual currents of his age. We should not mock older explanations simply because they were incomplete. They were steps. Without steps, later understanding does not arrive. Now let us return to the emotional centre of the question. Why does 1604 matter so much to modern people? Because it is the last obvious one. It sits like a marker on the timeline. Since Kepler's supernova, humanity developed calculus, steam power, electricity, photography, radio, rocketry, computers, satellites, particle physics, internet culture, and the unfortunate habit of checking messages during meals. All of that happened. No equally clear galactic supernova did. That contrast makes the gap feel personal. It spans the modern era. But we must be careful not to let visibility become reality. The absence of another obvious naked eye event does not mean the Milky Way stopped producing supernovae. Some may have occurred behind dust. Some may have been modestly visible and overlooked. Some remnants likely represent events not widely recorded. The 1604 event is the last clearly seen one, not necessarily the last one. That distinction matters enormously. It means Kepler's supernova may be the last time the galaxy gave us a clean public performance, not the last time stellar death occurred nearby. Think of a thunderstorm hidden beyond hills. If you do not see the lightning, storms still happen. Our galaxy has many hills, made of dust. Another reason 1604 remains valuable is calibration. Historical brightness estimates, timing of fading, and remnant measurements allow astronomers to compare models. It helps us understand Type 1a supernovae more broadly, and those supernovae are central tools for measuring cosmic distances. So an event seen in the age of quills and candlelight still informs precision cosmology. That sentence would sound absurd until you remember science is cumulative. Knowledge keeps receipts. There is also the simple wonder of continuity. Light from that explosion travelled thousands of years before reaching Earth in 1604. While it crossed space, civilizations rose and fell, languages changed, borders shifted, people were born, lived, and died unaware that a signal was approaching. Then one autumn it arrived, a new star in Ophiuchus. Humans looked up, some wrote notes. And centuries later, we still discuss it. The universe has excellent long-term timing. What would happen if an equally bright Milky Way supernova appeared now? Every telescope that could observe it would pivot. Space agencies would issue statements. Spectra would be captured within minutes. Amateur astronomers would contribute valuable imaging. Social media would become unusable for several hours. News anchors would learn the phrase Type 1a with mixed success. It would be magnificent. Part of that magnificence would come from the long wait since 1604. Silence gives contrast. Contrast gives impact. Yet the gap since Kepler's supernova can also mislead us into imagining something unnatural has happened. Perhaps the galaxy changed, perhaps supernova stopped, perhaps we are cursed by timing. More likely, several ordinary explanations overlap: random spacing, dust obscuration, unfavourable locations, human attention limits, detection methods that only recently became powerful. The 1604 event may simply be the last time probability, geometry and visibility all cooperated. That is less dramatic than cosmic conspiracy. It is also more believable. There is a final gentle irony here. Kepler helped describe planetary motion mathematically, revealing order in celestial paths. Yet the event named for him reminds us that not everything arrives on predictable schedules. Stars explode when physics demands, not when historians would prefer symmetry. So what happened to the last clearly seen supernova in our galaxy? A white dwarf likely reached catastrophe and tore itself apart. Its light crossed space and startled early modern observers. Its debris still expands. Its memory anchors our sense of the quiet since. And because it was the last obvious example, it naturally leads us to another question that sits just beneath the surface of this whole mystery. Was the centuries-long gap after 1604 truly unusual? Or are we simply unlucky observers living in a statistically normal pause between rare and inconveniently timed cosmic events? Perhaps the simplest explanation is often the least satisfying one. We like mysteries to have hidden mechanisms, secret causes, elegant conspiracies and dramatic reveals. We enjoy the thought that somewhere in the equations lies a profound reason the Milky Way has denied us a bright recent supernova. Maybe the galaxy changed. Maybe stellar evolution entered a quiet phase. Maybe we misunderstand everything, but there is another possibility. Maybe we are simply unlucky observers. That answer sounds modest, almost disappointing, yet it deserves serious respect. Much of science involves learning when a pattern is real, and when a pattern is what randomness looks like from too close a distance. Human minds are excellent at noticing streaks, gaps, coincidences, and suspicious timing. We are less naturally gifted at calmly accepting that chance often produces arrangements that feel meaningful. The long silence since Kepler's supernova may be one of those cases. To understand this, we need to separate averages from schedules. When astronomers say the Milky Way might host a few supernovae per century, that does not mean the galaxy runs a dependable service with departures every 47 years. Nature does not print timetables. It gives rates, tendencies, distributions, and probabilities. If a city averages 10 rainy days each month, rain does not politely arrive every third day. Some weeks are dry, then 3 wet days cluster together, and everyone complains about drainage. If a forest averages 1 large fire every few decades, there may be long quiet stretches followed by 2 in surprisingly short succession. If buses average every 10 minutes, someone somewhere is still waiting 25. Averages describe the long run, lives are lived in the short run. That mismatch matters. Suppose the Milky Way truly averages about 2 supernovae per century. Even then, the actual spacing between visible, well-placed, easily noticed events could vary dramatically. Some centuries might contain several, others might contain none that are obvious to people on Earth. Once dust, geometry and brightness differences are added, the gap between spectacular naked-eye events can stretch much longer than the underlying explosion rate suggests. So yes, we may be waiting inside a statistically ordinary pause. This becomes easier to grasp with a thought experiment. Imagine a jar filled with marbles representing years. Most marbles are ordinary years with no clearly visible galactic supernova. A few marbles represent years with one. Some of those are hidden by dust. Some happen near the apparent direction of the sun. Some are faint. Some are glorious and unforgettable. Now draw a random human lifetime from the jar. Many people would draw none. Some would draw one. A few lucky or unlucky souls, depending on sleep schedule, might get 2. From inside one lifetime, the pattern feels personal. From the jar's perspective, it is routine. There is another timing problem we rarely notice. Humanity's most advanced observing era is extremely recent. Electronic detectors, automated sky surveys, neutrino observatories, space telescopes, infrared all-sky monitoring, rapid data sharing, and continuous transient alerts are mostly products of the last few decades. That is not even a blink in galactic terms. So when we say, why haven't we seen one recently? Part of what we mean is, why hasn't one happened during the very short interval when our tools became extraordinary? That is a fair question. But it may also be a slightly impatient one. Picture someone arriving at a beach, opening a book, sitting down for 5 minutes, then asking why they have not yet witnessed a once-per-hour perfect wave. The wave schedule did not begin with their towel. Likewise, the universe did not arrange its events around the arrival of CCD sensors. There is also the observer location problem. We do not stand in a neutral place outside the galaxy with panoramic visibility. We live inside the dusty disk of the Milky Way, offset from the centre, surrounded by extinction, line-of-sight crowding, seasonal skies, weather systems, daylight, horizons, and a planet that insists on rotating at all times. This means even if supernovae occur at expected rates, the subset that become dramatic shared spectacles from Earth is smaller. Now combine chance with filtering. That alone can generate long dry spells. Human psychology, however, dislikes filtering. We prefer stories with causes. If no obvious supernova has appeared since 1604, many instinctively feel there must be a reason deeper than probability. Yet probability regularly produces surprising gaps. Casinos rely on this misunderstanding. So do lotteries, queues, and people convinced their toaster is behaving personally. Randomness can feel targeted. It is not. There is an illuminating comparison in astronomy itself. Meteors enter Earth's atmosphere constantly. Most are tiny and unnoticed. Occasionally a brighter fireball appears. Rarely, a spectacular event lights the sky over populated areas and becomes famous. If someone lived centuries ago and asked why no great fireball had appeared in their town lately, the answer might simply be timing and location, not cosmic shortage. Supernovae are rarer, of course, but the principle remains. Events occur. Observers sample imperfectly. Another layer of bad luck may involve historical timing. The last clearly seen galactic supernova, Kepler's supernova, happened before modern telescopes truly transformed astronomy. If an equally bright event occurred now, it would be one of the most studied phenomena in history. Every wavelength, every detector, every observatory would respond. Instead, we got one just early enough to be famous, but not fully instrumented. That is almost comically unfortunate. The galaxy gave us fireworks, we brought notebooks, then came centuries of waiting just as our cameras improved. There is a softer version of cosmic irony in that timeline. Still, luck can swing the other way. If a bright supernova appears tomorrow, future generations may view us as extraordinarily fortunate. They may say, imagine living at the moment humanity had mature observatories and a naked-eye galactic supernova at the same time. History often rebrands luck after the fact. There is also the matter of what counts as unlucky. If by unlucky we mean deprived of spectacle, perhaps yes. If by unlucky we mean unsafe, perhaps no. Many supernovae bright enough to amaze us would ideally occur at healthy distances. Too close, and radiation effects become more concerning. Too far, and the show is diminished. There is a sweet spot where the event is glorious but not hazardous. Waiting for the right supernova is rather like wanting thunder to sound impressive without striking the house. So perhaps caution is wise. Some likely candidates known to astronomy, such as Betelgeuse, generate excitement precisely because they are relatively nearby, and would create a memorable display if they exploded, yet not so close as to be catastrophic in the usual estimates. But soon, in stellar language, may mean within tens of thousands of years. That word continues to cause trouble. Betelgeuse dimmed dramatically in 2019 to 2020, and headlines rushed towards supernova fantasies. In reality, surface changes and dust offered better explanations. The event reminded us how eager we are for timing to favour us. We're waiting not just for any explosion, but for one aligned with our curiosity. That is a very human wish. Leak also shapes scientific careers. Somewhere there are astronomers who spent decades studying supernova progenitors, retired honourably, and missed the galactic event by 3 years. Somewhere future students may begin graduate school the week before the next one and become famous by accident. The cosmos does not distribute opportunities by fairness, it distributes them by occurrence. There is something strangely comforting in that. We often imagine the universe withholding things intentionally, but stars do not know we are waiting. They are not teasing us. They are following internal physics, binary interactions, mass thresholds, collapse conditions, and timelines longer than civilizations. No insult is intended. We simply are not on the guest list. And yet, observer luck can improve with technology. Even if no bright naked eye supernova appears soon, we are now capable of catching obscured events through infrared surveys, neutrino bursts, radio remnants, X-rays, and gamma rays. We no longer rely entirely on fortune plus clear weather plus dark skies plus someone looking up. That is progress. We cannot command events. We can reduce how often chance hides them. This distinction matters because unlucky observers once meant missing everything. Today it may only mean missing the public spectacle while science still captures the physics. Another useful thought experiment. Imagine 2 centuries identical in explosion rate. In one century, 3 supernovae occur behind thick dust on the far side of the galaxy. In another, one bright event occurs in a clear nearby region visible worldwide. Which century feels more active to humans? Obviously the second. But physically, the first may have hosted more explosions. Our sense of cosmic drama depends heavily on presentation. The galaxy is under no obligation to market itself effectively. There is also survivorship bias in historical memory. We remember spectacular visible events like 1006, 1054, 1572, and 1604 because they were obvious enough to enter records. Hidden or modest events are underrepresented. This can create the illusion that history once delivered frequent brilliant displays and modernity receives none. Perhaps history always included both. We mainly preserved the loud ones. That pattern is not unique to astronomy. It also describes family stories, politics, and restaurant reviews. So are we simply unlucky observers? Possibly, and perhaps largely. Unlucky in timing, because our instrument-rich era is short. Unlucky in placement, because we live inside a dusty disk. Unlucky in expectations, because averages mislead intuition. Unlucky in memory, because we compare ourselves to famous centuries. Yet luck is only half the picture. We are also extraordinarily lucky. Lucky to know what supernovae are. Lucky to understand stellar evolution. Lucky to possess detectors sensitive to particles once unimaginable. Lucky to map remnants of explosions no one saw. Lucky to live when astronomy can listen in wavelengths beyond vision. Lucky to be able to ask this question intelligently at all. That is no small privilege. If the next clear Milky Way supernova comes during our era, we may suddenly reinterpret centuries of silence as suspense. If it comes later, another generation inherits the excitement. Either way, the galaxy loses nothing by waiting. What if some recent supernovae were not absent, not delayed, and not merely hidden by chance, but happened quietly enough that we almost missed them altogether? Not every dramatic event announces itself dramatically. That may sound obvious once stated, yet it runs against a powerful instinct. We hear the word supernova and imagine a blazing new star dominating the night sky, bright enough to stop conversations mid-sentence and send half the neighbourhood outdoors in slippers. Sometimes that happens. Sometimes it does not. A supernova can be physically immense, historically important, chemically transformative, and still visually underwhelming from Earth. It may unfold behind dust, at awkward distance, in a crowded stellar field, or with lower than expected brightness. In some cases, the galaxy may have offered us a genuine stellar explosion while we barely noticed. This possibility changes the tone of our whole mystery. Perhaps we have not been waiting in silence. Perhaps we've been missing quieter knocks at the door. When people picture supernovae, they often imagine the brightest famous examples. Events like SN 1006 or the 1054 explosion that created the Crab Nebula were striking enough to enter human records clearly. Those events shape expectation. We unconsciously assume a galactic supernova must be obvious, but astronomy deals in ranges, not stereotypes. Some supernovae are brighter than others, some fade faster, some eject matter into dense surroundings that alters how they shine. Some are reddened and dimmed by dust, some happen where visible light struggles to escape. The word supernova describes mechanism families, not a single theatrical standard. This matters because if the Milky Way produced a moderate event in a difficult location, it might never become a universal public spectacle. Scientists could later identify the aftermath, while most people remained unaware anything extraordinary had happened. One of the strongest examples often discussed is G 1.9 plus 0.3, widely considered the youngest known supernova remnant in our galaxy. Based on its expansion, researchers estimate the explosion occurred only around a century or two ago, as seen from Earth. That is astonishing. A genuine galactic supernova may have happened in the modern era. So why did it not become famous? Because it lies near the galactic centre, where heavy interstellar dust severely obscures visible light. Even a powerful event in that direction can be dimmed dramatically. The explosion may have been there, real and energetic, while the sky above human observers offered little obvious fanfare. This is the kind of revelation astronomy specialises in. You ask why nothing happened, then discover something happened behind curtains. G 1.9 plus 0.3 is not the only reminder that remnants can reveal events history barely recorded. The Milky Way contains many known supernova remnants: shells, filaments, radio sources, X-ray clouds, expanding debris fields. Some correspond to historically documented explosions, others do not. Some are too old for written records, some occurred in eras or places where documentation was lost. Some may have been faint, hidden, or confused with other phenomena. The sky does not preserve headlines, it preserves debris. This creates a fascinating mismatch between physical reality and cultural memory. Human history remembers what was visible, discussed, and recorded. The galaxy remembers everything in gas, motion, and chemistry. The two archives overlap only partly. Another category of almost missed involves intrinsically faint explosions. Not every supernova releases visible light with the same efficiency. Some so-called low-luminosity supernovae are substantially dimmer than textbook examples. Others may collapse with much of the energy carried away in neutrinos rather than bright optical display. Imagine expecting fireworks and receiving a distant muffled flash behind fog. The event still occurred. Your expectations were the issue. Some massive stars may even undergo partial fallback events, where material initially ejected later falls back toward the forming compact remnant, reducing visible brilliance. In certain cases, a black hole may form quickly, and the outward display may be weaker than standard dramatic models suggest. Astronomy sometimes refers to possibilities like failed supernovae, where a massive star may collapse into a black hole with little bright explosion at all. Observationally, one proposed signature is simply a massive star disappearing. That is both scientifically thrilling and emotionally rude. You monitor a star for years, then it leaves without saying goodbye. If such events occur in the Milky Way, they would complicate the assumption that every stellar death becomes an obvious spectacle. There are also transients that imitate or blur categories. Some stars undergo giant eruptions without fully dying. events sometimes called supernova imposters. Eta Carinae famously erupted in the 19th century and became one of the brightest stars in the sky, yet survived. To observers at the time, such an eruption was extraordinary. To modern astrophysics, it was dramatic but not final. This means historical records of strange bright stars may include a mixture of true supernovae, novae, giant eruptions, and other transients. Likewise, some true but modest supernovae may have blended into the crowded category of something odd happened in the sky. Classification after the fact is hard. The universe labels poorly. Distance is another subtle thief of drama. A supernova on the far side of the galaxy can still be enormously luminous, but distance reduces apparent brightness. Add dust, and the result may drop below public notice thresholds. It may remain detectable with instruments, yet fail to become a cultural event. This can feel unfair until we remember scale. The Milky Way is around 100,000 light-years across. We are not centrally seated in a small dome. We are one neighbourhood resident in a sprawling city trying to notice a light turning on in a distant district through haze. Timing can also hide events in simpler ways. Suppose a supernova peaks near the apparent position of the sun in the sky. Daylight glare may conceal the brightest phase. By the time the object emerges into night skies weeks later, it may already be fading. Or imagine peak brightness during a season of poor weather across heavily populated regions, historically likely to preserve records. Clouds have quietly erased many observations. They remain undefeated. Modern detection systems help enormously, but even now subtle events can be missed initially. Automated surveys compare images and flag changes, yet crowded galactic fields are challenging. Variable stars, novae, artifacts, and dense backgrounds complicate searches. Some discoveries happen only after careful data review. The sky is vast. Software gets tired too. Infrared astronomy has become especially important because infrared light penetrates dust better than visible light. A supernova hidden optically may still glow detectably in infrared. Radio observations can later reveal expanding shock fronts. X-rays trace hot, shocked gas. Neutrino detectors can capture bursts from core collapse even when visible light is blocked. This means we are entering an era where almost missed may become less common scientifically, even if visually hidden events remain common culturally. That distinction matters. Science can notice what society does not. There is a psychological angle here as well. We often imagine discovery as instantaneous. Something happens, everyone knows. In reality, many discoveries are retrospective. Data are reanalyzed. Old images are revisited. Faint remnants are mapped. Distances are refined. Ages are recalculated. Only later do we realize we nearly missed something important. That is true in astronomy and in life often enough to be annoying. Consider how many galactic remnants were identified only through radio surveys. To human eyes, nothing obvious remained, but at radio wavelengths, shells and structures emerged clearly. A supernova that never became famous visually could still leave a loud radio signature centuries later. The universe sometimes whispers in one language and shouts in another. There is also the matter of expectation bias. If you tell people a supernova must be brighter than Venus, they will search memory for no such event and conclude none occurred. But if some are modest, reddened, low on the horizon, short-lived, or hidden near dense star fields, memory becomes unreliable. Many people miss planets visible for months. This is not an insult. It is a reminder that looking is not the same as noticing. Historically, dedicated skywatchers noticed far more than casual observers. Court astronomers in China, Islamic scholars across Middle East, and early modern European observers often knew the sky intimately. Today, professional systems replace much of that role, but casual familiarity with the sky is lower in many urban societies. A moderately obscured galactic transient today might first trend online not because people saw it directly, but because observatories announced it. That's a very modern form of noticing. There is something strangely comforting in the idea of hidden and faint supernovae. It means the apparent silence since Kepler's supernova may not indicate inactivity. The galaxy may have remained productive, dynamic, and occasionally explosive the entire time. We simply lacked the right seat, wavelength, weather, or attention. The silence then belongs partly to us, not to the stars. From where we stand, it can seem as though every galaxy except our own is having more fun. Open an astronomy news feed, and there they are again. Another supernova in some distant spiral galaxy. Another brilliant transient in a catalogue number nobody can pronounce comfortably. Another fresh explosion discovered by an automated survey before breakfast. Meanwhile, the Milky Way appears reserved, almost shy. That impression is understandable. It is also misleading. Other galaxies do not necessarily light up more often than ours in any dramatic absolute sense. In many cases, they simply light up more obviously to us. We are dealing less with a difference in stellar behaviour and more with a difference in viewpoint. And viewpoint in astronomy changes everything. To understand this, imagine trying to evaluate city traffic. If you stand inside a crowded neighbourhood, surrounded by buildings, alleys, parked cars and local noise, your sense of the city's total motion is partial. You know your street well. You know the corner shop delivery truck is late again. You know someone nearby owns an alarmingly enthusiastic motorcycle, but you do not see the whole city. Now imagine looking from a helicopter at night. Roads glow, bottlenecks stand out, movement patterns become clear. A single traffic jam flashes like a signal. That second perspective is much closer to how we observe external galaxies. The first is how we experience the Milky Way. We live inside our galaxy's disk, embedded among stars, dust, gas clouds, and line-of-sight clutter. We cannot step outside for a panoramic portrait. We observe our home galaxy from a complicated interior seat. That means bright events can hide behind dust, overlap dense star fields, occur in difficult directions, or be reduced in visibility by our own local conditions. By contrast, many other galaxies are seen from the outside. We view their overall shapes directly: spirals, ellipses, irregular systems, barred disks, starburst galaxies, interacting pairs. Against that cleaner backdrop, a supernova can appear as a new bright point where no bright point was before. That makes discovery much easier. A stellar explosion in another galaxy may be tens of millions of light years away, yet more straightforward to detect than one inside our own disk behind dust lanes. This sounds backwards until you remember geometry. Sometimes distance matters less than obstruction. Astronomers take advantage of this constantly. Automated surveys repeatedly photograph thousands or millions of galaxies. Software compares new images with older reference frames. If a new bright source appears, the system flags it for follow-up. In practical terms, other galaxies are monitored like neighbourhoods on a well-organised map. The Milky Way is more like trying to inventory your own house while living inside every room at once. Another factor is scale of observation. When surveys watch many galaxies simultaneously, even rare events become common in aggregate. Suppose one galaxy hosts only a few supernovae per century. Watch 10,000 galaxies, and suddenly explosions are happening regularly somewhere in your sample. This creates a psychological illusion. We hear about supernovae in distant galaxies often, and assume those galaxies must be more active than ours. Usually we are just seeing many lotteries combined. It is the same reason someone in a large city hears ambulance sirens often, while any one individual street may be quiet. Scale changes frequency of notice. There is also a selection effect built into headlines. News stories rarely announce that another normal galaxy did not explode this week. They announce discoveries. That means public awareness is skewed toward active examples. You're not reading galaxy behaves statistically as expected. No sudden brightness today. Though I admit that would be honest. Instead, we hear about SN 1987A, a famous nearby explosion in the Large Magellanic Cloud. We hear about bright supernovae in galaxies catalogued as NGC this or M that. We hear about rare superluminous events, peculiar transients, colliding stars and strange outbursts. The ordinary quiet vast majority receives less publicity, so our mental sample becomes biased toward fireworks. Dust remains one of the biggest reasons our own galaxy seems quieter. We have already discussed interstellar dust as a curtain, but it is worth revisiting here because the contrast with external galaxies is powerful. When we observe many spiral galaxies from outside, their dusty lanes are visible as dark bands crossing the disk. They are beautiful and dramatic in photographs. Yet because we are outside those systems, a supernova occurring on the near side or in a favourable region can still stand out cleanly. Inside the Milky Way, we're often looking along the disk through those same kinds of lanes from within. The path length through obscuring material can be immense. It is like admiring someone else's foggy valley from a hillside while standing in your own fog. One fog bank is scenic, the other is inconvenient. Another subtle point involves galactic type. Not all galaxies truly share the same supernova rate. Some do produce more explosions than the Milky Way. Starburst galaxies, for example, are undergoing intense episodes of star formation. They create many massive stars, and massive stars die young as core-collapse supernovae. Interacting galaxies, where gravitational encounters compress gas clouds, can trigger bursts of stellar birth and later elevated death rates. So yes, some galaxies genuinely are busier, but many of the galaxies where we detect ordinary supernovae are not wildly exceptional. They simply belong to large monitored samples. This distinction matters. We should not overcorrect and assume every external detection is only perspective. Sometimes a galaxy really is hosting an especially lively period. Nature allows both truth and bias at once. The famous Large Magellanic Cloud gives a useful middle case. It is close enough that SN 1987A became one of the best-studied supernovae in history. It was not in the Milky Way proper, but it was near enough to revolutionize astrophysics. Neutrinos were detected. Light curves were tracked in detail. The remnant continues to be studied decades later. Why did it feel so prominent? Because proximity helped. Because the location was favourable, because modern instruments existed, and because it happened outside our dusty galactic disk, in a nearby companion galaxy easier to view clearly. That combination was gold for science. If a similarly favourable event occurred inside the Milky Way, interest would be extraordinary. There is also the issue of contrast. A bright point in another galaxy appears against a relatively smooth background in images. In our own galaxy, especially near the plane, backgrounds are crowded with stars, nebulosity, variable sources, and confusing structure. Imagine placing a candle in a dark window across the street. Now place the same candle in the middle of Times Square. Same flame, different challenge. This is why modern galactic transient searches often rely on infrared monitoring, radio follow-up, and careful image subtraction techniques. The problem is not lack of events. It is separating them from a messy foreground and background. Then there is human romance with the distant. A supernova in another galaxy feels cinematic because of scale. A star exploded 50 million light-years away. It sounds grand. It is grand. But it can distract from equally important nearby phenomena hidden in less glamorous ways. A dusty remnant in the inner Milky Way may teach us more physics than a photogenic distant flare. Beauty and usefulness are related, not identical. Science learns to appreciate both. Our own galaxy may also suffer from familiarity bias. Because we live in it, we treat it as background. The Milky Way band has always been there. We normalize it. External galaxies, however, are discrete named objects with neat edges in telescope images. When one changes, it feels eventful. The home system becomes wallpaper. The distant stranger gets headlines. Humans do this socially too. Modern surveys such as those run by professional observatories and automated networks have dramatically increased the number of known extragalactic supernovae. Decades ago, only a modest number were catalogued annually. Now discoveries are routine because cameras are wide-field, software is fast, and archives are searchable. This technological revolution can make the universe feel more explosive than before. In reality, it is often more observed than before. That sentence explains many scientific eras. There is a delightful irony here. We once thought the heavens static because we lacked sensitive monitoring. Now we can feel overwhelmed by transience because monitoring is so good. Same sky, better tools, different emotional experience. So why do other galaxies seem to light up more often? Because we watch many of them at once. Because we often view them from outside. Because new bright points stand out clearly. Because surveys are designed to find exactly that. Because headlines favour discoveries. Because some galaxies truly are in more active star-forming phases. And because our own position inside a dusty spiral disk is observationally awkward. None of this means the Milky Way is lazy. It means home is harder to inspect. Somewhere in the Milky Way tonight, certain stars are living in their final phases. Not final in the human sense of next week or next year necessarily, but final in the broader astrophysical sense. Fuel supplies altered, interiors changing, outer layers unstable, clocks advancing toward endings that can only be delayed so long. This is one reason the long quiet in our sky should never be mistaken for safety, emptiness, or inactivity. The machinery of stellar evolution is always running. So if supernovae are not random magic tricks, which stars do astronomers actually watch? Which objects are considered plausible future candidates? And when we say soon, what on Earth, or rather beyond Earth, do we mean by that word? The first and most important clarification is that astronomers cannot usually predict the exact day a star will explode centuries in advance. Stars do not provide appointment cards. We infer likely futures from mass, age, chemical makeup, variability, environment, and theoretical models. In some cases, we know a star is massive enough to end in core collapse. In other cases, we know a white dwarf system may someday produce a thermonuclear event. But precise timing is difficult. That means, could explode soon, often translates to anything from tomorrow to 100,000 years. Which sounds evasive until you appreciate the scale involved. If a star has lived for 10 million years and has perhaps 10,000 left, astronomers may reasonably call that soon. Human beings may reasonably call that not useful for planning. Both perspectives are valid. The most famous name in this conversation is almost certainly Betelgeuse. It sits in the shoulder of Orion and is one of the brightest stars in the night sky. It is a red supergiant, swollen, luminous, unstable, and nearing the end of life compared with ordinary stars. Betelgeuse began far more massive than our Sun. Massive stars burn fuel quickly. They pass through stages of fusion far faster than smaller stars. Red supergiants represent a late evolutionary phase, where the outer layers expand enormously, while internal fusion proceeds through advanced stages. Eventually, such stars can collapse and explode as core collapse supernovae. So yes, Betelgeuse is a legitimate candidate. No, this does not mean panic. No, this does not mean keep shoes by the bed. Betelgeuse is roughly hundreds of light years away, with exact distance estimates refined over time. If it exploded, it would likely create a stunning astronomical display and not an extinction-level crisis. It could become visible in daytime and dominate the night sky for weeks or months, depending on details. That prospect alone keeps public imagination engaged. The star also helped create modern excitement in late 2019 and early 2020 when it dimmed significantly. Headlines raced toward the word supernova with remarkable athleticism. In reality, later studies strongly supported explanations involving surface cooling and expelled dust that temporarily blocked light. In other words, Betelgeuse coughed dramatically. The internet assumed obituary. Still, The episode served a useful purpose. It reminded millions that stars are dynamic objects, not decorative pins fixed forever overhead. Another notable candidate is Antares, the bright red heart of Scorpius. Like Betelgeuse, Antares is a red supergiant and massive enough that its final fate may involve core collapse. It is distant enough that a future explosion would likely be more spectacular than dangerous, though timing remains deeply uncertain. These giant red stars fascinate us because they wear their age visibly. They are bloated, variable, losing mass, and unstable in ways smaller stars are not. They look like elders of the sky, yet not every supernova candidate glows red and obvious. Some blue supergiants or other evolved massive stars may also be in late stages. The famous SN 1987A came from a blue supergiant in the Large Magellanic Cloud, surprising expectations at the time. Nature again reminded astronomers not to become too attached to tidy categories. Massive stars can evolve in more than one route depending on rotation, metallicity, binary interactions and mass loss, which means the waiting list is messier than celebrity rankings. Binary systems deserve special attention because many stars are not solitary. A massive star with a close companion may transfer material, lose its outer layers, spin differently, or evolve in unexpected ways. Such systems can produce stripped envelope supernova, unusual remnants, or timings different from isolated star models. In simpler terms, stars with companions lead more complicated lives. This should surprise no one. Then there are Type 1a candidates, which are less photogenic beforehand but no less important. These involve white dwarfs in binary systems or mergers of two white dwarfs. A white dwarf itself is compact and comparatively faint. You would not glance up and say, "That discrete little point is planning a thermonuclear future." Yet some such systems are among the galaxy's true explosive possibilities. If a white dwarf steadily gains mass from a companion and approaches the critical threshold for instability, runaway fusion may eventually destroy it in a Type 1a supernova. Alternatively, two white dwarfs in a decaying orbit may merge after losing energy through gravitational radiation. These are harder for the public imagination because they lack the visual drama of a giant red star. There is no swollen crimson beacon announcing danger, just dense stellar remnants conducting quiet, technical business until catastrophe. Quite modern, really. One historically famous recurrent nova system often discussed in this context is T Coronii Borealis. It periodically brightens due to accretion-driven eruptions and has drawn interest because such binary systems reveal how mass transfer can destabilize white dwarfs. Whether any specific system becomes a Type 1a supernova soon is another matter, but they help us study the route, and again, soon remains elastic. Astronomers also watch Wolf-Rayet stars, extremely hot, massive stars that have shed much of their outer hydrogen envelopes through powerful winds. These stars are advanced, stripped, and in some cases likely future core collapse candidates. They can produce energetic explosions and, under certain conditions, perhaps even more exotic events, such as long gamma-ray bursts if rotation and geometry align. A Wolf-Rayet star sounds like a villain from an old novel. In reality, it is a stellar warning label. Examples in our galaxy include systems such as Gamma Velorum and others, though exact fates depend on mass and binary evolution. Now let us address the emotional trap hidden inside the word waiting. It sounds as though astronomers are gathered beneath the sky, tapping watches impatiently. That is not quite right. The galaxy contains many candidates at different stages. Some may explode in the next millennium, some in the next 100,000 years. Some may lose enough mass to avoid expected routes. Some in binaries may surprise us. Some hidden stars in dusty regions may already be closer to collapse than famous visible stars. The most likely next Milky Way supernova may come from an object most people have never heard of. That possibility is wonderfully humbling. We often assume the headline star gets the headline ending. The universe does not guarantee branding consistency. Location also matters greatly. A candidate near us but at safe distance would produce a glorious show. One far across the galaxy may still be scientifically valuable, but visually muted. One toward dusty inner regions could explode and remain disappointing to casual eyes while thrilling every observatory on Earth. So the phrase next supernova actually hides several different questions. Next physically to occur, next to be detected, next to be obvious to the public, next to be beautiful in the night sky. These may not be the same event. There is another reason timing is hard. Late stellar interiors are complex. Convection, rotation, shell burning, mass loss, magnetic fields, and binary influence all complicate models. We can often identify broad life stage, but the precise final countdown remains elusive. It is rather like knowing a mountain has winter snow and avalanche risk while not knowing the exact hour a cornice will break. Physics sets conditions. Triggers can be subtle. Still, monitoring improves yearly. Space telescopes, interferometry, spectroscopy, neutrino detectors, and time domain surveys help astronomers track variability, mass loss, pulsations, and changes in candidate stars. If one nearby massive star entered truly terminal instability, we might see warning behaviour, though exactly what warning signs would appear remains uncertain. Imagine getting advance notice that a star is about to become world news. Scientists would be delighted. Sleep schedules would suffer. There is also a philosophical pleasure in waiting. For most of human history, people did not know stars had life cycles at all. Now we can look at specific objects and say, with grounded confidence, this one will end violently someday. That is astonishing progress. We move from mythic lights to predictive astrophysics, and yet the final step, when exactly, still resists us. Some mysteries shrink, some simply become better defined. The waiting game also teaches patience across scales. Human culture prizes immediacy, refresh rates, notifications, instant footage. Stars operate on million-year tempos interrupted by seconds of catastrophe. If we demand celestial events on human schedules, disappointment is guaranteed. The universe is not slow, it is differently timed. So which stars could explode soon? Likely some red supergiants such as Betelgeuse or Antares on broad astronomical scales. Likely some lesser-known massive stars hidden in dusty star-forming regions. Likely some Wolf-Rayet stars nearing collapse. Likely some white dwarf binaries inching toward Type 1a thresholds. Possibly systems we have not characterized fully yet, almost certainly not according to our preferred timetable. Few stars have achieved modern celebrity quite like Betelgeuse. It has name recognition, distinctive colour, seasonal visibility, dramatic rumours, and the rare talent of causing headlines whenever it appears to have a slightly unusual day. Most stars burn for millions of years in dignified anonymity. Betelgeuse, by contrast, has become the one many people know personally enough to mispronounce with confidence, and it is easy to understand why. Betelgeuse is bright, nearby by stellar standards, visibly reddish, and located in the constellation Orion, one of the easiest patterns in the sky for many observers to recognize. When Orion rises in winter skies across much of the world, Betelgeuse marks the hunter's shoulder. It does not hide in some obscure catalogue entry, requiring a graduate degree in emotional resilience to locate. It sits in one of the most familiar constellations on Earth. That visibility matters. People pay attention to what they can actually find. Add to this the fact that Betelgeuse is a massive evolved star nearing the end of its life, and it becomes irresistible. Here is a star you can point to with your own eyes that is genuinely expected to explode someday as a supernova. Someday, however, is doing a lot of work in that sentence. Let us begin with what Betelgeuse really is. It is a red supergiant, a class of enormous stars that started life with far more mass than our Sun. Massive stars live quickly. They burn hotter, brighter, and much faster than smaller stars. After exhausting hydrogen in their cores, they expand dramatically and move into later evolutionary stages. Their outer layers swell to tremendous sizes. Their atmospheres become extended and unstable, and they begin losing material through strong winds and eruptions. Betelgeuse fits that description beautifully. If placed at the centre of our solar system, its outer atmosphere would extend to a distance comparable to the orbit of Mars or beyond, depending on how one defines the fuzzy edge. This is not a neat solid ball with a sharp surface. Red supergiants have diffuse extended atmospheres. Still, the scale is staggering. Our Sun is vast by everyday standards. Betelgeuse makes it look modest. Despite its size, Betelgeuse is not especially old compared with smaller stars. Massive stars spend fuel quickly. Estimates vary, but it's likely only around 10 million years old or so, which is youthful compared with the Sun at roughly 4.6 billion years. This often surprises people. Large stars are cosmic prodigies with short careers. Small stars are patient marathoners. Because Betelgeuse is advanced in its evolution, astronomers expect it to end as a core collapse supernova. At some point, fusion in the core will no longer provide enough pressure to resist gravity. Collapse will occur, followed by an explosive ejection of outer layers. Depending on the final core mass, it may leave behind a neutron star or possibly a black hole. That much is broadly understood. The frustrating detail is timing. Could Betelgeuse explode tomorrow? In principle, yes. Could it wait 100,000 years? Also, yes. This is why every article declaring imminent doom or guaranteed spectacle should be read with calm amusement. We know the destination. We do not know the departure minute. Betelgeuse became especially famous during the Great Dimming of 2019 to 2020. Observers noticed that the star's brightness dropped dramatically, becoming much fainter than usual. Public excitement surged. Perhaps this was it. Perhaps the long-awaited supernova was beginning. Perhaps the sky had chosen our era after all. The actual explanation turned out to be more subtle and, in its own way, more interesting. Evidence suggests Betelgeuse likely ejected material from its surface, which then cooled and formed dust that temporarily blocked some of the star's light from our perspective. Combined with natural pulsations in brightness, this produced the striking dimming. So rather than exploding, Betelgeuse appears to have sneezed dust into our line of sight. Astronomers were delighted. Headline writers were inconvenienced. That event taught an important lesson about red supergiants. These stars are dynamic, convective, unstable places. Their surfaces are not calm like polished bulbs. Giant cells of rising and falling gas move through their outer layers. Pulsations occur. Mass loss happens. Dust forms. Brightness varies naturally. In other words, Betelgeuse is dramatic even when it is not dying. That alone keeps observers interested. It also means interpreting changes is difficult. A star with a restless atmosphere can mimic signs that, to an eager public, sound like final warnings. But variability is part of normal life for such stars. The challenge is distinguishing ordinary instability from truly terminal instability. We are not perfect at that yet. Distance adds another reason Betelgeuse fascinates people. It is relatively close, roughly a few hundred light-years away, though exact estimates have varied with measurement methods. In galactic terms, that is nearby. Not next door, but in the same broad neighbourhood. Close enough that a future supernova would be spectacular. Far enough that it is not generally considered a severe existential threat. That combination is ideal for public enthusiasm. People enjoy cosmic drama at safe distances. If Betelgeuse exploded, it could become visible in daylight and dominate nighttime skies for weeks or months. It might rival or exceed the brightness of the full moon at peak in some estimates, though details vary with models. Even if less extreme, it would certainly be extraordinary. Imagine Orion suddenly gaining a brilliant new beacon where a familiar red star once stood. People who never normally look up would look up. Children would remember it for life. Astronomers would cancel vacations. Yet Betelgeuse is not guaranteed to be the next supernova we see. This is worth repeating. Fame does not create priority in astrophysics. The next galactic supernova could come from an obscure star hidden in dust, a binary system few casual observers know, or a region most people rarely notice. Betelgeuse is simply the most famous plausible candidate. It is the celebrity on the watch list. There are scientific reasons it is studied intensely beyond public curiosity. Because it is close and large, Betelgeuse can be imaged in ways most stars cannot. Telescopes have resolved surface features and asymmetries. We can study its atmosphere, winds, variability, and mass loss in unusual detail. It serves as a laboratory for understanding how massive stars behave near the ends of their lives. That matters not only for Betelgeuse itself, but for red supergiants generally. Every insight gained here helps interpret more distant stars we cannot examine as closely. It is a reminder that famous objects are sometimes genuinely useful, not merely famous. There is also something psychologically appealing about a visible countdown object. Humans like focal points. The next supernova could be any of millions of stars under uncertain conditions is scientifically honest but emotionally unsatisfying. Watch Betelgeuse is simpler. It gives waiting a face. We do this in many fields. Complex climate systems become one storm. Economics becomes one stock ticker. Astronomy becomes one red star in Orion. The truth is broader, but symbols help attention. Betelgeuse also benefits from seasonal timing. In many northern and southern latitudes, Orion is a beloved winter constellation. People notice it during clear, cold evenings. A star regularly seen in comfortable cultural contexts is easier to care about than one hidden in a crowded summer field near the galactic centre. Visibility shapes affection. There is an irony in Betelgeuse's popularity. If it were somewhat more distant and obscure, it might be scientifically similar yet publicly forgotten. Instead, because it glows in a famous constellation and occasionally behaves strangely, it became the star everyone watches. The universe did not assign marketing departments. Geometry did. What signs would truly precede a supernova from Betelgeuse? That remains uncertain. Some models suggest increased mass loss, unusual variability, or changes in emitted neutrinos might occur near the end, but robust short-term predictive markers are limited. We cannot yet read a red supergiant like a calendar. If Betelgeuse collapses, one of the earliest definite alerts may come not from visible light, but from neutrino detectors. These nearly massless particles can escape the collapsing core before the shock reaches the surface and before bright optical light surges outward. Meaning science might know first, then the sky would catch up. That possibility is delightful. Imagine astronomers quietly announcing, "Please look at Orion tonight." There is another healthy caution worth adding. Because Betelgeuse is variable, future dips or surges in brightness will almost certainly happen. Each may trigger fresh speculation. Most will not indicate immediate explosion. A living red supergiant is noisy data. We should admire the behaviour without assuming every cough is farewell. Still, one day the speculation will be correct. Not because every rumour is wise, but because stars eventually keep their appointments with physics. Whether that occurs in our lifetimes is unknown. Whether it occurs eventually is certain. So why is Betelgeuse the star everyone is watching? Because it is close. Because it is bright. Because it is familiar. Because it is evolved. Because it once dimmed dramatically. Because it offers a plausible future spectacle visible to ordinary eyes. And because waiting for the next Milky Way supernova feels easier when you can point at a candidate from your backyard. Yet even Betelgeuse is only one possibility among many. If any supernova finally appears in our galaxy, famous star or obscure one, the next question becomes immediate and wonderfully practical. What would such an event actually look like from Earth on the night it begins? One evening the sky would seem normal right up until it wasn't. That is perhaps the most honest place to begin. A Milky Way supernova, if visible from Earth, would not arrive with cinematic warning music. The air would feel the same. Trees would move the same way in the wind. Streetlights would hum. Someone somewhere would still be looking for their keys. Then, depending on where in the galaxy the event occurred and how bright it became, a new light would appear where no such light belonged. And once noticed, it would be impossible to ignore. What it looked like from Earth would depend on several things: distance, direction in the sky, dust between us and the event, the type of supernova, and whether it happened in daylight or darkness for your location when the light first became obvious. Those details matter enormously. But let us imagine a favourable case first, because it helps the mind settle around the scale of what we mean. Suppose a star a few thousand light years away in the Milky Way underwent a bright supernova with relatively clear visibility. It might first appear as an unusually bright star, perhaps one that seemed to emerge suddenly over a few hours or days depending on the type of event. Night after night it could brighten further. Then people would begin asking questions. Was that always there? No? Are you sure? Yes. Soon it might rival the brightest planets. Then it could exceed them. In an especially bright case it might cast faint shadows at night. If close and luminous enough, it could even become visible in daylight as a pale but distinct point. Imagine looking into a blue daytime sky and seeing a star. That alone would be unforgettable. For many people, the emotional impact would come before the scientific one. Humans are accustomed to the sky changing slowly. Sunrise, sunset, moon phases, seasonal constellations, the occasional meteor, an eclipse if fortunate. But a brand new bright object appearing among familiar stars breaks expectation immediately. The heavens are not supposed to improvise so boldly. Historically, that is why ancient observers took such events seriously. A new star was not merely pretty, it was disruptive. Modern people would likely respond in a mixture of wonder, memes, and frantic searching. Astronomers, meanwhile, would become the busiest calm people on Earth. Now let us talk brightness more carefully. A supernova in our galaxy could range from modestly striking to astonishingly brilliant depending on distance and extinction. If it occurred on the far side of the galaxy behind thick dust, it might appear only as a bright reddish star or even be difficult to see with the naked eye, while instruments went wild with excitement. If it occurred nearer and unobscured, it could rival the moon in brightness at peak, though not all events would. Some estimates for a future Betelgeuse supernova, for example, suggest it could become extraordinarily bright, perhaps visible in daylight for an extended period. The key point is this: there is no single standard appearance. The Milky Way contains many possible stages and distances. Still, even a moderate visible galactic supernova would likely become one of the most discussed sky events in modern history. Colour would also evolve. Early on, some supernovae may appear bluish-white due to extreme temperatures. Over time, as the expanding material cools, the colour can shift. Dust along the line of sight may redden it. Different wavelengths peak at different stages. To the naked eye, many would simply look like a brilliant star whose brightness slowly changes over weeks and months. No flickering explosion in real time. No fireball tearing visibly across the sky. That is another misconception worth clearing gently. The event is explosive in physics, but from Earth it would mostly look like a star brightening, shining intensely, then gradually fading. Space-scale, smooth drama into patience. There would be no visible blast wave racing outward to the eye. The expanding debris moves fast by physical standards, thousands of kilometers per second, but at stellar distances angular growth is tiny. Telescopes over months and years would track change. Human eyesight would mostly perceive a bright point, yet what a point. If it appeared in a familiar constellation, cultural impact would be even greater. Imagine Orion suddenly altered because Betelgeuse had transformed. Imagine Cassiopeia gaining a beacon brighter than any nearby star. Familiar patterns would feel rewritten. Constellations survive by habit. A supernova interrupts habit. Night photography would become a global hobby overnight. Social media feeds would fill with phone images, telescope images, over-processed images, blurry images through kitchen windows, and at least one image that was definitely a street lamp but received strong support online. This too is part of the modern sky. Professional observatories would observe across every wavelength possible. Optical spectra would reveal the expanding material's composition and velocity. Infrared telescopes would probe dust and cooling ejecta. Radio arrays would watch shock waves interact with surrounding gas. X-ray observatories would monitor high-energy aftermath. Neutrino detectors might have provided early warning already if it were a core collapse event, meaning by the time many people first saw it, scientists might already have celebrated privately for several frantic hours. There would also be practical questions. Would it harm Earth? Would nights become hot? Would tides change? Would pets know first? The answers in most realistic, visible but safe scenarios are reassuring. A supernova bright enough to amaze us is not necessarily dangerous. The galaxy is large. Many candidate stars are distant enough that the event would be primarily visual and scientific rather than catastrophic. Brightness does not equal threat. A floodlight across a valley can look intense without burning the village. Still, the exact risk depends on type and distance, which is why every real event would be analysed carefully. How long would it last? Longer than many people expect. Peak brightness might persist for days to weeks, depending on the event. Fading could continue over months. Some remnants remain visible in telescopes for years. Ancient records describe historical guest stars seen for many months, sometimes even in daylight for part of that time. This is not a meteor's brief thrill. It is a season of changed skies. Imagine children beginning a school term with one sky and ending it with another. Imagine months of stepping outside and seeing that extra light waiting where it was never meant to be. That persistence would shape memory. There is something profound about a temporary celestial object lasting long enough to become normal, then fading again. Human adaptation works quickly. We would go from astonishment to routine faster than seems respectable. Have you seen the new star? Yes? It's still there. I know, I need groceries. That may sound cynical, but it is affectionate realism. Humans normalize wonders rapidly. It is one of our strangest talents. Different locations on Earth would experience it differently. If the supernova occurred in southern skies, southern hemisphere observers might enjoy better views. Northern observers might have lower horizons or seasonal challenges, and vice versa. Cloud cover, urban light pollution, and local geography would matter. For some, it would be a nightly companion. For others, an occasional glimpse between buildings and weather systems. A supernova near the Galactic center could appear in a dense star field rich with Milky Way glow. In darker regions, it might stand alone more dramatically. Context changes perception. Then there is the emotional layer no instrument measures well. Many people would feel small. Many would feel connected. Many would think about time, mortality, history, and the fact that the light reaching us began its journey before many modern institutions existed. If the star were thousands of light years away, the explosion itself happened thousands of years ago. We would only now be receiving notice. That delay often stuns people more than the brightness. You're not watching it happen now. You're watching news arrive late. Astronomy does this constantly, but a visible supernova would make the lesson vivid for millions. The next morning, newspapers and websites would explain terms like light year, red giant, white dwarf, core collapse, and shock wave. Teachers would revise lesson plans. Planetariums would overflow. Amateur astronomy clubs would gain new members. Some would remain long after the headlines faded. A single star could recruit generations into science. This has happened before in quieter ways. Eclipses inspire observers. Comets awaken curiosity. A galactic supernova would do so at another scale entirely. What would it look like in the final months of visibility? Gradually dimmer, perhaps still obvious at first, then comparable to bright stars, then ordinary stars, then binocular object, then telescope target. The world would slowly lose interest as brightness faded, while scientists remained deeply engaged because the evolving spectra and remnant physics become richer over time. The public often loves the entrance. Science loves the whole performance. Eventually, years later, telescopes would resolve expanding nebular structures, perhaps a future remnant for later centuries to admire the way we admire the Crab Nebula or Kepler supernova remnant now. Future people might visit observatories to see the remnant of the great supernova of our century. That thought carries a pleasant continuity. So what would a Milky Way supernova look like from Earth? Usually not like a movie explosion, more like a new star brightening beyond reason, a point of light that grows impossible, a familiar sky made briefly unfamiliar, months of visible reminder that stars live and die, a shared global experience written overhead. Walk through the night sky with the naked eye, and you might think supernovae are rare memories. We have spoken of historical events, long gaps, hidden explosions, and the waiting game for the next bright outburst. From that perspective, stellar death can feel occasional and distant, almost mythical. But look with telescopes tuned to the right wavelengths, and a different truth appears. The Milky Way is littered with evidence. Not dramatic, fresh explosions perhaps, but their remains. Across the galaxy are expanding shells, tangled filaments, glowing clouds, magnetic shock fronts, neutron stars, pulsars, enriched gas, and invisible scars in interstellar space. These are the remnants of stars that already ended. The sky may seem quiet tonight, yet it is full of aftermath. This changes the emotional shape of our mystery. We ask, why haven't we seen one recently? The galaxy replies, you're standing among the ruins. A supernova remnant forms when material blasted outward by the explosion plows into surrounding gas and dust. The ejected debris races outward at thousands of kilometers per second. It shocks the interstellar medium, compresses magnetic fields, heats gas to immense temperatures, accelerates particles to high energies, and creates structures that can persist for thousands or even tens of thousands of years. The brilliant flash may last weeks or months. The consequences can last ages. This is why remnants matter so much. They are the long memory of brief violence. One of the most famous examples is the Crab Nebula, born from the supernova observed in 1054. To ancient observers, a guest star appeared in the sky. To us, nearly 1,000 years later, the remnant is still expanding. Inside the Crab Nebula sits the Crab Pulsar, a rapidly rotating neutron star left behind when the original massive star collapsed. It emits beams of radiation like a lighthouse, sweeping across space as it spins. So one stellar death gave us both a glowing nebula and a cosmic clock. That is an efficient use of catastrophe. Viewed through modern telescopes, the Crab Nebula is intricate and active. Filaments of gas glow in visible light. Synchrotron radiation from charged particles spiraling in magnetic fields fills it with energy. It is not a static grave marker. It is a continuing system. Another well-known remnant is Kepler supernova remnant, the aftermath of the last clearly seen naked-eye supernova in our galaxy. The original star that exploded has long since vanished, but its debris shell remains observable in X-rays, radio and optical wavelengths. Centuries after the flash that startled Johannes Kepler and his contemporaries, the event still teaches us physics. That sentence captures something lovely about astronomy. Light fades, evidence lingers. Then there is Tycho supernova remnant, linked to the star observed by Tycho Brahe. Like Kepler's remnant, it continues expanding into surrounding space. Modern X-ray observations reveal shock fronts, high-energy particles, and the chemistry of the explosion. An event once debated philosophically now appears in scientific images filled with plasma physics. History ages well when telescopes keep improving. Some remnants were never seen clearly by humans at all. That may be even more interesting. Consider Cassiopeia A, one of the brightest radio sources in the sky. It is thought to come from a supernova that occurred around the late 17th century, though no famous widespread naked-eye observation survives. Perhaps it was obscured, perhaps faint, perhaps poorly placed, perhaps simply missed. Yet today, Cassiopeia A is among the most studied remnants in astronomy. The galaxy does not require applause to make history. G1.9 plus 0.3, which we discussed earlier, is another powerful reminder. Likely the youngest known supernova remnant in the Milky Way, it suggests a relatively recent explosion hidden by dust near the galactic centre. Again, the pattern repeats. We thought there was silence, then found debris. Many more remnants populate catalogues. Vela supernova remnant, Puppis A, Cygnus loop and numerous others. Some are nearby and sprawling. Some are compact and young. Some are obvious in radio. Some shine in X-rays. Some are beautiful in optical filaments. Some hide until a particular wavelength reveals them. Each one says the same thing in a different accent. A star died here. Why do remnants look so different from one another? Several reasons. The type of supernova matters. Core collapse explosions from massive stars often occur in environments shaped by stellar winds and prior mass loss. Type 1, A explosions involving white dwarfs may occur in cleaner surroundings. The density of nearby gas changes how the shockwave evolves. Magnetic fields influence particle acceleration. Age matters enormously. Young remnants are compact and energetic. Older ones become broader, fainter, and more blended into the interstellar medium. No two ruins weather identically. Another fascinating role of remnants is chemistry. Supernovae forge and disperse heavy elements. As the debris expands, it enriches the galaxy with oxygen, silicon, sulfur, iron, and more. Future stars, planets, moons, and perhaps life itself can form from material influenced by ancient explosions. So remnants are not just graveyards, they are supply chains. The calcium in bones, the iron in blood, the silicon in rocks and electronics, the oxygen bound into worlds and atmospheres, much of it traces back through generations of stellar processing and dispersal. You're not merely looking at remnants, you're partly made from older ones. That is literal, not metaphorical. Supernova remnants also accelerate cosmic rays, high-energy particles travelling through space. Shock fronts act like giant natural particle accelerators. These particles eventually reach Earth's atmosphere, contributing to showers of secondary particles and ongoing astrophysical mysteries about origin and transport. The ruins are energetic. They do not simply sit there. Some remnants contain compact leftovers. Neutron stars, pulsars, and perhaps black holes mark the collapsed cores of massive progenitors. Finding these remnants helps reconstruct the original explosion. Did the star leave a spinning neutron star? Did it collapse more completely? Was the blast asymmetric? Astronomers become detectives of old violence. We examine debris, measure motion, map chemistry, locate compact survivors, and infer the lost star. There is something profoundly human in that effort. Give us scattered fragments, and we will build a story. Observing remnants also teaches humility about timescales. A supernova flash may be gone before a child becomes an adult. The remnant can remain visible for millennia. Civilizations rise and change while the shell keeps expanding. Imagine future historians living under skies where the memory of our era is vague, yet telescopes still image the remnant of a supernova we watched. That is entirely plausible. Remnants also reveal why our question about not seeing one recently can be misleading. if the galaxy contains hundreds of known or candidate remnants, then supernovae have clearly occurred many times. The issue is not whether they happen, the issue is whether the bright phase overlaps with human observers, clear sightlines, and preserved records. The galaxy keeps producing evidence long after it stops producing headlines. There is another subtle point. Some remnants may have become so old and diffuse that we no longer recognize them easily. As shockwaves slow and merge into surrounding gas, boundaries blur, structures fade. Catalogue completeness is imperfect. We likely know many remnants, but not all. Meaning the historical count of explosions inferred from visible records is almost certainly an underestimate. The sky remembers more than we do. Modern astronomy finds these remnants through many methods. Radio surveys reveal synchrotron shells, X-ray observatories detect hot plasma, optical telescopes image emission filaments, infrared traces dust heated by shocks, gamma-ray observatories probe energetic interactions. Each wavelength contributes a piece. No single window tells the whole story. That lesson repeats throughout our journey. Visible light alone is not enough to understand the Milky Way. If human eyes were our only instrument, many remnants would remain unknown, and the galaxy would seem calmer than it truly is. Instead, we now know we inhabit a system marked by recurrent stellar death and renewal. A busy neighbourhood, quietly scarred. There is even comfort in that phrase scattered around us. It sounds ominous until you realise scale protects us. These remnants are vast and distant. They are part of the normal ecology of galaxies. Stars form, evolve, explode, disperse material, and seed future generations. We live in the product of previous cycles. One day our sun will not explode as a supernova, but it too will return material to space in gentler fashion. Nothing stays fixed forever. The galaxy is a recycler with dramatic methods, so when people ask why we have not seen many recent supernovae, the better reply may be to point outward and say, look at the remnants, look at the Crab Nebula, look at Cassiopeia A, look at Kepler's shell, look at Tycho's debris, look at radio arcs and X-ray clouds hidden from naked sight. These are receipts. The Milky Way has been paying its stellar bills all along. If the next supernova in the Milky Way happened tonight, we would not meet it the way ancient skywatchers did. They met sudden changes with eyes, memory, and careful notes. A new star appeared, and humanity reacted after the light arrived. We would experience something very different. The visible brightening might still astonish us, but by the time many people stepped outside to notice it, instruments around Earth could already be ringing alarms, because modern astronomy no longer waits only for light. We now watch the universe through many messengers: neutrinos, X-rays, gamma rays, radio waves, infrared radiation, gravitational measurements, automated optical surveys, and networks of telescopes linked across continents. The next nearby supernova may first announce itself not as a bright star in the sky, but as data. And that is one of the most exciting changes in the history of observation. We have moved from seeing events to anticipating them, not predicting them years ahead, unfortunately. The stars still refuse to provide calendars. But in the final moments of some explosions, especially core collapse supernova, nature leaks clues before visible light escapes the star. The most famous of these clues are neutrinos. Neutrinos are tiny, nearly massless particles produced in huge numbers during violent nuclear processes. They interact so weakly with matter that trillions pass through your body every second without complaint, permission, or practical consequence. They stream through planets, stars, and walls, as though these objects were mostly suggestion. During the core collapse of a massive star, however, neutrinos are released in astonishing numbers. In fact, most of the energy of the collapse is carried away by neutrinos rather than visible light. That means when a star's core catastrophically fails, neutrinos can escape almost immediately from deep inside the star, while photons, the particles of light, may still take time to fight through outer layers before the visible flash emerges. So in some cases, neutrinos arrive first. That creates a remarkable possibility. Astronomers may know a star has exploded before the sky visibly changes. This is not science fiction. It has already happened in a limited but historic way with SN 1987A in the Large Magellanic Cloud. Neutrino detectors recorded a burst associated with the event, providing direct confirmation of theoretical models of core collapse supernovae. Only a few dozen neutrinos were detected. That was enough to make history. Since then, detectors have become larger, more sensitive, and more organised. Facilities such as Super Kamiokande, Ice Cube Neutrino Observatory, and others around the world stand ready to catch future bursts. These instruments are extraordinary. Some use enormous tanks of ultra-pure water deep underground. Others use Antarctic ice itself as a detector. They watch for faint flashes created when a rare neutrino interaction finally occurs. To the casual eye, they may look like improbable plumbing projects. To physics, they are ears pressed against the stellar heartbeats of the galaxy. If a core collapse supernova occurred somewhere in the Milky Way, modern neutrino detectors could register thousands or even tens of thousands of events, depending on distance and detector capability. That would be a scientific treasure beyond exaggeration. It would reveal details of the collapse process, neutrino properties, energy release, and the behaviour of matter at extreme densities, and importantly it could happen before the visible brightening peaks. There is even an alert network called Supernova Early Warning System, often shortened to SNEWS. Its purpose is beautifully practical. If multiple neutrino detectors register a burst consistent with a nearby supernova, an alert can be sent rapidly to astronomers worldwide. Imagine receiving the message, "A star has just died. Look up soon." That may be one of the greatest notifications ever designed. Neutrinos are not the only silent warning. X-rays can also become important, though timing depends on the event. In some supernovae, shock breakout occurs when the explosion-driven shockwave reaches the star's surface. This can release a burst of ultraviolet or X-ray radiation before or alongside the dramatic visible brightening. Catching shock breakout is scientifically valuable because it gives direct information about the progenitor star's size, outer layers, and explosion dynamics. It is brief, it is elusive, and modern instruments actively search for it. Space-based observatories sensitive to X-rays and gamma rays can detect sudden energetic transients that ground-based eyes never would. This is why the next supernova may begin as a conversation between satellites before it becomes a conversation between neighbours. Infrared astronomy adds another layer of readiness. If the supernova occurs behind thick interstellar dust, visible light may be dimmed heavily. Infrared wavelengths penetrate dust much better. Telescopes observing in infrared could reveal an event hidden from ordinary sky watchers. So even if many people saw no spectacular new star, science might still capture the explosion clearly. This is an important emotional adjustment. The next great galactic event may be visually subtle, but scientifically magnificent. Radio astronomy also becomes crucial after the initial blast. As ejected material slams into surrounding gas, shockwaves accelerate particles and generate radio emission. Arrays such as Very Large Array and other radio facilities can map expanding remnants, probe circumstellar environments, and track how the blast evolves over time. Radio waves tell stories long after bright optical headlines fade. Then there are gravitational waves. While the next Milky Way supernova is not guaranteed to produce a strong, easily detectable gravitational wave signal, asymmetric core collapse could generate ripples in space-time detectable by facilities like LIGO or its partner observatories if conditions are favourable. Imagine that. Neutrinos from the core, light from the surface, ripples in space-time from the collapse, multiple messengers from one dying star. This is what astronomers mean by multi-messenger astronomy, and the next galactic supernova could become one of its greatest triumphs. We would not merely see the event, we would hear it in particles, trace it in radiation, and feel it in geometry itself. Are we ready? In many ways, yes. Far more ready than any civilization before us. Automated sky surveys now scan the heavens nightly. Robotic telescopes can slew rapidly to alerts. Amateur astronomers worldwide own equipment once reserved for professionals. Data pipelines compare new images to archival references within minutes. Observatories coordinate internationally. Space telescopes monitor multiple wavelengths. Communication is nearly instantaneous. If something bright and clear happened, humanity would mobilize scientifically at astonishing speed. There would be no centuries-long mystery about what occurred. There would be terabytes by sunrise. Yet readiness has limits. We still cannot predict exact timing. We cannot monitor every hidden stellar core directly. We cannot guarantee weather for ground observatories, nor ensure every instrument is online at the crucial moment. A supernova behind dense dust near the galactic center would still challenge optical observers. Hardware fails, funding cycles exist. Humans misconfigure things at inconvenient times. The universe remains capable of surprise. That is healthy. It keeps science humble. There is another kind of readiness worth considering: public readiness. Would people respond with wonder or fear? Probably both. Some would marvel, some would panic briefly, some would ask if it affects Wi-Fi, some would insist it was staged. This too is part of modern civilization. But many would also become curious. Planetariums would fill, teachers would revise lessons, children would ask what stars are made of. People who never looked up might begin. A supernova could become a scientific doorway for millions. That may be one of its gentlest gifts. We should also appreciate the patience built into these systems. Neutrino detectors may wait decades without a galactic burst. Survey telescopes compare quiet skies night after night. Space observatories monitor apparently uneventful fields. This can look dull from the outside. It is not dull. It is preparedness. Fire stations are quiet until they are not. Modern astronomy often works the same way, and when the call comes, the response will be extraordinary. The first neutrino spike might trigger silent software checks, then cross-confirmations between detectors, then alerts to observatories. Telescopes would pivot. Astronomers would abandon lunches, sleep, vacations, and perhaps balanced emotional states. Within minutes, spectra would be taken. Within hours, papers would begin drafting themselves in nervous laptops worldwide. Meanwhile, most of humanity would still be waiting for darkness. That contrast is lovely. The data race begins before the sky show. If the event were from Betelgeuse or another known nearby candidate, the drama would intensify because everyone already knows where to look. But even an obscure dusty region explosion would produce immense scientific value. We no longer depend on beauty alone. We can learn from hidden things. So, are we ready to catch the next one? Ready enough to do wonders? Ready enough to hear particles from a collapsing core? Ready enough to image the shockwave's aftermath across wavelengths? Ready enough to coordinate globally in real time? Ready enough to turn one stellar death into decades of knowledge? Not ready enough to schedule it? That privilege remains with the stars, and when it finally happens, after all the alerts, spectra, particles and excitement, we may still end where humans always end with the sky, standing outside, looking up, wondering what it means to witness something so old, so distant, and so suddenly bright. Night after night the sky can seem unchanged. The same familiar constellations return with the seasons. Orion rises, then leaves. Cassiopeia turns around the pole. The Milky Way stretches overhead where darkness allows it. Stars hold their places so reliably that generations build stories around them. Farmers once planted by them, sailors steered by them, children still learn shapes from them. against daily human life, the heavens feel steady. That steadiness is persuasive. It tempts us into believing nothing much is happening. Yet over the course of this journey we have uncovered a different truth. The sky is not still, it is not empty, it is not inactive. It is simply operating on scales of time, distance, and subtlety that do not always match human senses. That difference creates the illusion of silence. We asked why we have not seen supernovae recently in our own galaxy. At first, the question sounds almost accusatory, as though the Milky Way owes us spectacle. Where are the exploding stars? Why has nothing happened? Why does every other galaxy seem to get the headlines? But once we looked more carefully, the mystery softened. Supernovae likely do occur in the Milky Way at roughly expected long-term rates. Some are hidden behind dust. Some happen near the crowded galactic centre. Some may be dimmer than the famous historical examples. Some leave remnants we detect centuries later in radio waves or X-rays. Some may have taken place while human observers were distracted by weather, daylight, wars, archives, or the ordinary business of being alive. The issue was never necessarily absence. Often it was visibility. This is a comforting lesson far beyond astronomy. Sometimes nothing seems to happen because we are looking through fog. Sometimes the evidence is present in forms we do not yet know how to read. Sometimes quietness belongs to the observer, not the world. The Milky Way has been making and ending stars for billions of years. Massive stars burn quickly and collapse. White dwarfs wait in binary systems for unstable futures. Shock waves move through gas clouds. Heavy elements are forged and dispersed. Future stars and planets form from material shaped by older stellar deaths. Even our own bodies carry atoms whose story likely passed through ancient stars. So when we say the galaxy seems calm, we are speaking from a very local perspective. We are tiny, brief creatures living inside an active system so large that most of its events occur elsewhere or elsewhen. That is not depressing, it is clarifying. We also discovered that modern astronomy has changed the terms of waiting. Ancient observers needed bright, visible light to know the sky had changed. We now have neutrino detectors, infrared surveys, radio arrays, X-ray observatories, automated telescopes, and global alert systems. The next supernova may first arrive as particles through rock, signals through software, or faint wavelengths invisible to the eye. The universe once had to shout, now it can whisper, and we are finally learning to listen. There is something deeply human in our impatience for the next great event. We want to be the generation that sees it. We imagine stepping outside to find a new star blazing where none belonged. We imagine months of changed skies, schoolchildren remembering the moment forever, scientists losing sleep joyfully, and people who never cared about astronomy suddenly asking excellent questions. That hope is understandable. Wonder likes appointments. The cosmos does not. Maybe the next bright galactic supernova comes next year. Maybe it waits centuries. Maybe it already happened behind dust, and only later will its remnant reveal the truth. Maybe an obscure star no one talks about will become the most important object in the sky overnight. Maybe Betelgeuse keeps us guessing for far longer than headlines would prefer. All of these possibilities fit what we know, and somehow that uncertainty makes the sky feel more alive, not less, because a perfectly predictable universe would be easier to manage but harder to love. The real sky keeps secrets, it delays answers, it rewards patience. It reminds us that knowledge is often the art of waiting attentively. There is also a gentler perspective available here. We do not need a supernova tonight for the cosmos to be interesting. The stars already shining above you are active furnaces. Some of the light reaching you left before modern nations existed. Some stars you see may already have changed in ways we do not yet know because the news is still travelling. Even an ordinary night sky is full of delayed revelations. That is extraordinary enough. Still, one day the waiting will end. Some detector may trigger deep underground. Astronomers may receive an alert before dawn. Telescopes may turn as one. A point of light may grow where memory insists none should be. News anchors may practice unfamiliar star names. Millions may step outside together, and for a little while, humanity will share a sky that has visibly changed. If that happens in our lifetime, it will feel like a gift. If it happens later, it will still be a gift to someone. Either way, the galaxy loses nothing by taking its time. So as you settle into the quiet of this evening, perhaps carry one final thought with you. The silence above is not emptiness. The calm is not inactivity. The darkness is not absence. The sky is not silent. It is patient. And somewhere beyond sight, behind dust lanes, across spiral arms, within dense stellar fields, among stars whose names we know and many we never will, the next bright message is already on its way,